and greetings in the love and light of the infinite creator. I'm Andrii, and joined here with today's Dan and Stan and Ivor, and then Dan will be doing a presentation. Well, Dan, go ahead, introduce it.
Yeah, my name is Dan Gowin with Electron Power Technology, part of the Dan and Stan Energy Show, and the presentation we're going to do today is basically we're going to talk about new energy systems, looking at some old things to talk about new things, and basically more likely how we're going to perform the energy transition over to what we call the new world. So that's this presentation for the company. Okay, next slide. Any questions so far?
I'm still seeing the first slide.
Okay, here we go. So obviously this presentation is simply for educational purposes only. So nothing here should be used as investment advice, strictly for educational purposes only. We'll be showing information from some other companies in here. We identify what those companies are in the slide. Okay. So in order to understand how an energy transition might be possible, we first must understand the problem. We must understand energy storage. All batteries are rated in watts per kilogram, and all fuels are rated in BTUs per pound. Converting to joules per kilogram brings into focus these energy storage devices. Now we can understand how to substitute one energy storage device for another. The only fuel not on this chart is nuclear fuel, which is rated at greater than 94 million BTUs per pound. That's billions of joules. So what I've done here is I've taken these different types of energy storage device, even a log, you can consider, a wooden log is considered an energy storage device, and basically converted them over to a value that we can all agree and understand and agree with what's going on. So for example, if you look here, I've updated it. We got the new sodium ion batteries, which has a greater energy density than lithium ion batteries. The positive there, of course, sodium is salt is much more prevalent. The lower joules per kilogram for the sodium ion battery, 1,368,000 joules per kilogram. But if you can see, you have to look at it. So if you're going to try to replace the gasoline and diesel and so forth with an energy source or a fuel that have much higher energy content in all of them, down at the bottom you see there, you've got hydrogen as 120,210,000 joules per kilogram. So if you're going to replace gasoline, diesel, jet aircraft, right, with something that's equal to, if not greater than, the question is why would you go back to something like a battery when it's very obvious that you probably want to go forward with something like hydrogen would be a logical choice.
Like that, and I would say the everything about aviation is weight. So because this chart is made in joules per kilogram, the most energy dense is hydrogen. So it's a natural for aviation.
Yeah. Mm-hmm. I mean, shouldn't be a mystery. We used hydrogen to go to the moon. It's no mystery to me as an engineer why we use hydrogen as fuel to get us there, because that has the greatest bang for the buck, or bang per kilogram, or bang per pound. So as a fuel, it's a very logical choice.
It's just I know it's harder to store than like the liquid fuels.
Well, there's a lot of people have a lot of preconceptions that aren't correct. And we're going to go into we're going to go back in history and basically put all those preconceptions to the side. There's a lot of technology out there, old technology and also new technology that most of the public doesn't realize exists.
Okay.
So I'm going to start off with something that's old, and it's this stuff called coal gas. So what is it? Well, it's basically a reaction between carbon and water to produce hydrogen and carbon monoxide gas. So it was discovered in 1609 by Flemish scientist John Baptista von Helmont, described as wind spirit. In 1860 and 1681, John Becker of Munich discovered spirit of coal could destroy iron pipe upon prolonged contact. That was kind of the down aspect of actually discovering this thing that was hard to basically contain. I think that some of the concerns that you've talked about, Andrii. In 1787, Lord Dundonald lit his house at Culcross, Scotland. He discovered you could use copper tubing or bronze fittings to no effect when using the gas. So basically, right off the bat, there was a solution to this. Basically, the hydrogen would destroy the iron pipes, but they discovered that you could use copper or brass without any ill effect. In 1792, William Murdoch, later known as Murdoch, discovered by using a new device, the bubbler, You could facilitate new ways of purifying, storing the gas. By adding moisture to the gas, this would aid the cloth and leather fittings and gaskets used at the time. Cloth and leather would swell and thus seal the gas pipe work. So they had an issue with the gas leaking out of the pipes back at that time, and that was solved by just basically pumping the gas through basically water, a big tank full of water. It would actually purify the gas and add moisture to it. And the real reason was caused by because they were using cloth and leathers for gaskets and fittings and valves and so forth at the time. In France, Philippe Le Bon patented a gas fire in 1799 and demonstrated street lighting in 1801. Any questions so far?
So, well, I know that syngas, it's also can be produced from biomass, from my understanding. Yeah. Okay.
Yeah, there's a lot of things you can, anything with coal. We're going to talk about that. Coal, wood fittings, trimmings, biomass, a lot of things.
Carbon.
Anything with carbon, with water, you can turn that into hydrogen and carbon monoxide. So it's also called town gas, water gas, synthesis gas.
Okay.
Cool. So what is coal gas? Other demonstrations followed in France and the United States, but is generally recognized that the first commercial gas plant was built by the London Westminster Gas Light and Coke Company in Great Peter Street in 1812, laying wooden pipes to illuminate Westminster Bridge with gas lights on New Year's Eve in 1813. Let's see. In 1816, Rembrandt Peale and four others established the Gaslight Company of Baltimore, the first manufactured gas company in America. The first German gas plants were built in Hanover in 1825, and by 1870, there were 340 gas plants in Germany making town gas from coal, wood, peat, and other materials. In 1850, every small to medium-sized town and city had a gas plant. For providing street lighting. Subscribing customers could also have pipe lines to their houses. By this era, gas lighting became accepted. Gas light trickled down to the middle classes and later came to gas cookers and stoves. The 1860s were the golden age of coal gas development. Scientists like Cook and Perkin cracked the secrets of organic chemistry, reveal how gas is made and how its composition. Every town in North America and Europe with a population greater than 10,000 had town gas by 1899. George Westinghouse invented the natural gas system in the 1890s. His intention was to save lives. A number of people used town gas to commit suicide in addition to home poisoning. So believe it or not, people would actually go home to their gas stove and turn the gas on, open the door, and actually stick to half their body in the oven to kill themselves. The natural gas system was deployed in the U.S. in 1950. By 1966, all the town gas plants had been shut down and converted to natural gas, except for Indianapolis and Honolulu. England had to convert it to natural gas in 1970 upon discovery of the North Sea oil field. North Sea went into terminal decline over 20 years ago. Many of the British Parliament are rediscovering the old town gas system. So when you look at pictures and paintings like Victorian England, those gas lanterns they have, that was not natural gas. That was a mixture of hydrogen and other gases. So it's hydrogen, methane, carbon monoxide, and so forth. Any questions so far?
No, that makes sense.
Yeah, so I'm trying to say there was this hydrogen system. In fact, it was the first gas that was discovered by mankind. And it was actually in use long before any other before they discovered that there was gas associated with oil.
Because it was part of the syngas.
Yeah, well, that time they called it town gas, but the technical term is syngas, which is a mixture of carbon monoxide and hydrogen. So, right,
cool.
So, so this is Citizens Gas and Coke Company. I'm sorry. Yeah. Constructed in 1908, the Indianapolis Gas and Coke plant on a 22-acre site along Prospect Creek was a facility was built to supply Indianapolis and the surrounding area with town gas. It also supplied coke, or a product of coal burned in oxygenless ovens, to various steel plants around the country. They used it for coke for making steel. At the time of its construction, the state-of-the-art facility was the largest in the United States. It contained 2 massive coke batteries and a huge syngas processing division, along with cooling and ammonia towers, power plant, and gasometer. The down to 2014 had been supplying a high to approximately 6 million people in the Indianapolis area for over a century. The factors contributing to the shutdown were the quality of the coal. Producing steel is all about the quality of the inputs. Most steel foundries today use refinery coke, which is a much higher purity of carbon.
Okay, so Citizens Gas, is this different from town gas then?
No, it's a company.
Oh, it's a company. Oh, okay,
It's
I
called
see.
Citizens Energy Group. They're the company here in downtown Indianapolis. They
Oh, okay.
actually own this old Coke company. What I'm trying to tell you is I've actually burned hydrogen in my home. As a personal note,
Hmm.
I have a gas hot water heater and a gas furnace here in my house. One of the
Hmm.
things I'd have to do in the fall is I'd have to open up the little door of my hot water heater and take my vacuum hose and basically suck out the ash, because this Coke gas, it's called Coke gas, is actually kind of dirty and it would leave
Oh, okay.
residue behind in my hot water heater and my furnace. But
Oh,
since
wow.
they've shut it down in 2014, I haven't had to do that. So the gas is much cleaner. That's how I know
Hmm.
I was actually burning hydrogen in my house.
Oh, I see. Okay,
Yeah.
cool. Hmm.
Yeah, so that's one of the, like I say, have things that people don't realize that are out there.
Hmm.
Yeah, most of the equipment you see here has already been removed, so they're off of Prospect Creek. That's just a big open area. You have to remember this is all contaminated. It's a hazmat site. The more according to the EPA, there's between 3,000 to 4,000 of these old gas plants the public utilities still own, and they can't sell the land to the public because it's contaminated.
Hmm.
Yeah.
Would
So
they be able to retrofit it and use it for syngas later?
well, you probably could, or you could. We'll talk about that using it for something else.
Okay,
So
sure.
this is a place that's called Perry K. It's a town gas plant built in 1870 in Indianapolis. It produces syngas for their primary customer, Eli Lilly. So it still runs today. The old town gas system was designed around the gasification of coal by grinding coal and water together. Then heat is introduced. Carbon and water is transformed into carbon monoxide and hydrogen. Perry K's syngas is 40% carbon monoxide, 6% hydrogen. By 1873, this plant provides syngas, water gas to well over 1,200 street lanterns in downtown Indianapolis. They also provided gas for 47,000 homes, as was the case in many of the towns and cities in the world at that time. In 2016, the plant was converted from gasification to steam reforming of natural gas. Eli Lilly uses the syngas to polymerize plastic coatings on pills, methanol, and as a starting place for many drugs. Gasification of carbon is over 400, and it's actually over 400 years old. When Eli Lilly's production line is idle, the syngas is stored underground under downtown Indianapolis in a water well. In addition, Perry K provides steam and chilled water to all the buildings in downtown Indianapolis. This was my first power plant when I went to work for IPL back in 1998. Was this old syngas plant? Um,
Hmm.
yeah, so yeah, it was kind of a surprise to me to find it, and it goes back to history. Indianapolis Power and Light, they started as Indianapolis a gas light company, and they're providing gas to all these safety lights in downtown Indianapolis. Uh, Colonel Eli Lilly started using the gas in his, for example, his first store used to be down on Meridian Street. They moved it inside the facility. So Eli Lilly's about 3 blocks to the east of this facility. And they moved Colonel Lilly's original store is actually inside the corporate building there. So you can go in there and you can see the gas lanterns. It's like walking back into Victorian England. Where this plant is located in downtown Indianapolis, it's between the convention center and Lucas Oil Stadium. So if you show up in Indianapolis to watch an NFL football game, this plant is right across the street. The other aspect of this plant, you can see the smokestacks up there. I've actually been up there on top. There's maybe warm air that comes out of there. It doesn't belch out pollution because almost all the hydrocarbons are turned into this syngas. And of course, Eli Lilly uses that syngas to build make all the drugs and so forth that they make.
So that water, that's steam that we're seeing in the picture.
Well, it's hot.
Oh, yeah.
I mean, steam reforming. What it is, I'll tell you exactly what it is. They take a big pipe. It's packed full of nickel ball bearings. They basically burn some gas to heat this thing up to 500 degrees Celsius. They boil water in a big tank, inject natural gas and steam into that pipe, and that converts it into carbon monoxide and hydrogen. They also have what's called water shift, which is where they turn some of the carbon monoxide into hydrogen. That basically turns the carbon. It's a reaction between carbon monoxide and water. Then the output of that is carbon dioxide and hydrogen. So they add a little bit more hydrogen to the gas because Lilly prefers a gas that's much more rich in hydrogen gas. So a lot of people have asked me about what's my experience in the hydrogen business. Well, it's from this old town gas plant that was built in 1870.
Mm-hmm.
You've got a lot of people out there talk about things like embrittlement, leaking, you can't scale it, those type of things, not realizing that there's this infrastructure out there that's comes from a different age, from the Victorian age. So
Mm-hmm.
To reemphasize, we're talking about pre-Civil War is when this all started around the world.
Yeah, well,
Wow.
for example, Baltimore, you're talking about 1817. And we'll talk about at the end. I'll show you some of the gas lanterns there in Baltimore. 1817. basically the city of Baltimore, still to this day is producing town gas to some things there in Baltimore. So yeah, you understand Baltimore. You're talking about Baltimore, Philadelphia, Boston, New York City, Chicago, San Francisco. We were talking about Honolulu. Honolulu had a gas plant there also. Okay. So I'll give you some more modern stuff. So Wabash Valley Power Plant was brought online in 1991. Wabash Valley turns anything with carbon into syngas, which in turn is burned in 4 GE7HA gas turbines. The turbines, in addition, power 3 steam turbines through a Herzog, which is a heat recovery steam generator. Wabash Valley uses garbage from farm waste, wood pellets, even refinery coke as source material for its gasifier. The plant currently is adding a Haber ammonia plant to its capabilities. This plant requires greater than 500 tons of carbon material per day just to maintain its economics. The sorting of trash and other materials is a main endeavor just to make sure bottles and cans don't end up in the gasifier. So this is how you industrialize, or how you do large scale hydrogen production, is in plants like this. This is in Terre Haute, Indiana. You'll find that the Department of Energy is definitely neck deep in this facility.
And one thing I pointed out too is the only way you make one of these things economical is to scale it to this scale, because small scale gas fires are too costly to operate to make them realistic for to use. But you get to this scale and produce, now you can make some cheap electricity and gas.
So what is the scale that we're talking about here? Like, how many people, how many customers would you need?
Well, we use 500 tons a day for this one, right?
This is 500 tons. You need at least 100 tons a day. It also depends. Like
100 tons of coal?
Their primary customers,
100 tons of waste product.
Eli Lilly doesn't care what the cost is.
Yeah, rubbish, anything combustible.
Okay.
Cow manure.
100 tons a day. That's quite a lot.
Yes.
Yeah. So I guess that would be a kind of a regional,
right,
hub.
Well, here, let me give an example. The Philadelphia Gas Light Company was formed in 1823. By 1824, they were providing gas to 1,800 gas streetlights and providing town gas to more than 2 million houses. Well, for example, I talked about the Coke plant, the Citizens Gas and Coke plant that was here in Indianapolis when they shut it down in 2014. They were providing gas for more than 6 million people in the state of Indiana. So you're talking about systems that scale into the millions of homes, is what I'm trying to tell you.
I see.
Okay, we'll go to the next one here. So syngas can be turned into many different types of plastic. This is a process for making most plastics before the age of oil. In fact, the petrochemical industry adopted most of its processes from the old syngas system. Unfortunately, the U.S. only produces enough biomass to make the equivalent of 2 million barrels per day of transportation fuel. If we use trash as the feed material for gasification processes, maybe we could produce 6 million barrels per day of transportation fuel. Coal gasification is where our modern chemical industry has came from. The technology is 416 years old. The U.S. consumes 20 million barrels per day in crude oil for transportation fuel. So if you look down at the bottom, you got that syngas. The methanol, what they use is copper oxide. Zinc oxide is the catalyst that forms methyl alcohol. Mobile oil back in the 70s developed a process where you turn methyl alcohol into actually a form of gasoline. That's petrol. Polyolefins are types of waxes. Methyl acetates are different types of plastics, usually like adhesive tape. DME is dimethyl ether. It's a fuel that's actually the perfect fuel for the diesel engine. It has a cetane rating of 55. Formaldehyde can be used to create like a Bakelite plastic. An acetic acid is a concentrated form of vinegar. It's used in a lot of different processes, including, for example, making RTV with silicone rubber. If you smell that, like that vinegar smell, that's what that's from. Of course, ethylene for making high-density polyethylene plastic. IGC stands for Integrated Gas Combined Cycle. That's a Wabash plant that you saw, and then steam and power, that'd be like Perry K. It's a combined, Perry K is a combined plant. They use the heat from the syngas process to drive for steam to drive a steam generator. Of course, you've got hydrogen from ammonia chemicals, fuel cells, syngas, iron reduction. There's an alternative process for making steel that doesn't use coke. It uses the syngas for reducing iron oxide down in the steel. It's actually a much cleaner process. The problem with making coke is turning coal into coke is all the impurities in the coal, and those impurities end up in your steel. But if you use like syngas to do it, then you reduce your impurities that you might have in the steel. A much better process, believe it or not, is actually using hydrogen, because you can produce 99% pure hydrogen and therefore increase the purity of making steel. There's synthetic natural gas, and then the Fischer-Tropsch process that was developed by the Germans during World War II. One of the reasons why it was so difficult to defeat Nazi Germany is because the country had 320 town gas plants scattered all over Germany, and all of them had the ability for making petrol and diesel and plastic parts like Bakelite for like machine guns and radios and things like that. So
to capsulize this particular slide is, if you have syngas, you pretty much have an oil well. I mean, all the things that we think of that you need to make, whether from fuel to plastics, you can make from syngas, and you can make the syngas from rubbish or anything that's combustible. And there you go. So I look at this and say, well, not that we're going to stop burning oil because of greenhouse gases, but we're going to run out of oil, at least easy to get oil at some point. What are you going to do to make plastics and wax and diesel fuel? And well, it's syngas. So as we start looking at, and the key to syngas is the hydrogen piece. So taking it from Dan's first slide to this, the energy density of hydrogen is so great that once you got the syngas, now you got all these other products you can produce.
I know Charlie has a question.
Go ahead,
Charlie. Go ahead. Charlie, you got to unmute.
It's the same question.
Oh.
That was exactly what I was wanting to ask. If you have enough coal, and I guess the United States has a whole lot of coal, you can do whatever you want. You can make diesel, right? Can we make diesel at scale? Could we
as a matter
run
of
the
fact,
country on coal and this?
Charlie, as a matter of fact, that's what the Department of Energy is planning on. At the very end of the presentation, I'll show you a website at the Department of Energy. What the biggest problem with the power plants we have is actually the quality of the coal. For example, that coke plant I showed you, it was shut down because the quality of the coal was too low. But this technology, like Wabash, was actually built to basically turn lignite into these gases. And one of the things I
lignite,
talked about,
you can even use crappy lignite.
Yeah, you can use crappy lignite, or you can also they'll also talk about using advanced oil field services recovery from doing carbon capture from the process. Because the process actually lets you remove the carbon dioxide, chemically from the system.
Yeah.
But
incidentally,
yeah, they're actually planning on it. They're actually planning using these type of systems. And I try to explain to people, plastic is too important. You look at your laptop, your cell phone, ink, any of those things are made from plastics. I can see a time when plastic's going to become very valuable, and this is the system we're going to use for making plastics. That's what I'm trying to tell you.
Incidentally, anybody cares, I'm camping. There's a Columbia River Gorge. Can you see it?
Yeah. Wow. So you're out west. Yeah. Oh, okay,
yeah. I live we're in Oregon, and I live in the other end of Oregon. And Dan, I had another question earlier. In your first graph, you showed oxygen, not air, but oxygen coming in to the whole system as an input.
Yeah. I can tell you what they do. They have a big compressor, and they compress the air, and they compress the air to 550 psi. And what happens? The nitrogen turns into a fluid, and then they drain that out, and then what's left over is the oxygen, and then they inject oxygen in this system. They use a compressor to separate the air from the nitrogen air.
How much could you make a gallon of diesel using this whole system from coal? How much?
I have a good idea. The Germans, their data that they have shows 100 tons of coal for 1 ton of diesel. So it's an inefficient way of making fuel.
Sure is.
Yeah, you're better off just making plastics, is what I'm trying to tell you. Or like Lilly, they make drugs and things like that, value-added products. You could also use this system to recycle your plastic, by the way, because it'll burn in the gas.
So our drugs can be started with city trash,
Yes.
and run through all this stuff and
Yeah.
make.
Right. As a matter of fact, the Lily's actually planning on that. They're rebuilding the gasifier and the coal chute, right? And what they're thinking of, Lily's thinking 10 years from now, they're not going to be able to economically buy natural gas, so they're going to have to go back to the old gasification process. And they're planning on using biomass and maybe garbage to supply the plant, so they can get their syngas. That's what Lily's thinking internally in the company.
I'm wondering if we have estimates on how many billion barrel equivalents of coal there are left, the usable coal.
Yeah,
A
I
lot.
don't know. I know Steve St. Angelo is trying to figure that out right now. Steve might be a good person to ask that.
Okay.
The answer is a lot.
Well,
Yeah, we have a lot of lignite, something like 300 years worth of lignite. So, yeah.
Yeah, but my understanding is those hundreds of years, that's based on current consumption rates. So if we were to replace it with others, that would drastically go down.
Yeah, if we were to ramp this up, that would change the number. So,
all right.
Okay.
We want to continue this.
Next one. Okay. So,
one thing about this, the previous slide was we don't have the conversion efficiencies on here, but maybe
you'll have to. Yeah, I'll show you a website at the end of this, Andrew. I'll show you a website you can go to, and that way you can take a look at. And here's what the Department of Energy says about the process. So, understand, I'm just talking about stuff I know because I worked in the power plant. I don't know what the conversion rate is. All I know is Lilly uses this syngas for all those internal things for making drugs. And remember, I worked at Lilly for about 8 years also. So.
Oh, okay. All right. Thank you.
Yep. Yeah, when we get to the end, I'll show you the Department of Energy site. So I'll let you actually surf to the site on Google on your computer.
But yeah, from my memory, it's about 40 to 60% efficient for each stage, like converting it from biomass to syngas and from syngas to Fischer-Tropsch.
Yeah. Well, I can tell you, as far as the gas turbine, the combined cycle, the efficiency on this plant for burning syngas in the gas turbines and the steam turbine, the combined cycle, is 57% efficiency burning syngas to produce electricity. It's a 781 megawatt power plant that produces power on the power grid today. Very efficient. Any questions?
No, that's good.
Okay. So this is a chart talking about the electricity demand in the United States, how much electric power we consume in the United States. The U.S. consumes an average of 500 gigawatts of electricity per hour. It oscillates between 400 gigawatts to 540 gigawatts. Remember the brass paradox? It will become very difficult to add more generating capacity load to the power grid. It has to do with the complexity of the power grid. Usually in the spring and the fall, so the lowest part of the year, our consumption. Our highest level of consumption is usually in the summertime when everybody's using air conditioning. So, and that's just the lower 48. I didn't go into Hawaii or Alaska.
Yeah, this is just a few week in September.
Right. I understand. I already know. For example, the Chinese, they consume more than a terawatt of electricity per hour. Number 3 on the list would be India. India consumes about 300 gigawatts of electric power per hour. At one time, Japan and Germany were neck and neck at 100 gigawatts, but Germany electricity consumption has dropped down to 75 gigawatts. So I can actually measure the fact that German economy is actually shrinking because they're using less electric power.
The one thing we talked about too, Dan, is that we're not just talking the megawatts, but if you start to look at intermittent renewables like wind and solar, you can't even achieve these levels because of frequency stability on the grid, not just voltage stability, correct?
Yeah. Well, you and I talked about before, we have lots of data that shows that whenever your wind or solar gets above 15% on the grid, it causes frequency instability, and that'll actually knock out other generating sources. So, for example, the problem they had there in Portugal, Spain, and parts of France, even though we haven't got the final report, actually what caused the outage, basically, when I first looked at I said, okay, my first suspicion was the frequency stability, and I've got some of the original data, and it looks like the frequency stability was a big issue. Now they talk about some of the solar, but I'm looking at basically some of the inverters, because remember, wind power and your solar produce DC, and you have to turn that into AC, and you use inverters. And one of the bigger problems we have in power grids is building inverters up to this megawatt size, versus like an M6000 50 megawatt gas turbine you can fit in the back of a semi truck. It achieves frequency stability because it's it's 2 tons worth of spinning metal, so it's able to achieve frequency stability because it's just a big piece of metal spinning. Any questions so far?
There's a question from the YouTube. Entropy Juggler asks, the syngas processes and products are interesting, but obviously there are many entropic stages losses. The coal is much less energy dense than oil, so how much will societal velocity have to drop?
Well, I disagree with you. The coal is
Yeah.
not energy dense. It was on the first.
Agree.
Oh, okay.
Yeah, coal is about between 9 to 12,000 BTUs per pound, versus like diesel. Diesel's 18,500 BTUs per pound. Diesel's
So-
a much denser energy source than coal is.
Okay. Well, they were saying coal is much less energy dense. So are
Yeah,
you agreeing? Or yes? Okay. All right. Anyways, well, we can go on.
okay. All right. So we'll get to the next slide, which was really what reason why I showed this is for actually the next slide. So
Yeah.
Mhm.
Oh, and the reason we're talking coal is because that's the best example. But this is all gasification. You can gasify anything with carbon in it, rubbish, manure. I mean, you can gasify anything that burns. You can gasify into this process, not just coal.
yeah, so I'm showing here a chart from the Department of Energy. It has to do with something called geothermal. And according to the Department of Energy, the U.S. could replace all of its generating assets with EGS geothermal power plants. EGS is Enhanced Geothermal System. GWE stands for gigawatt. So what I'm trying to tell you is the United States Department of Energy is telling you that all solar, everything we have out there, we can actually replace what we call enhanced geothermal systems. Enhanced geothermal systems actually comes from horizontal drilling and fracking technology.
Can you again say what GWE is? You cut out there momentarily.
GW means gigawatts electricity. GWE.
Gigawatts electricity. Okay. Mm-hmm.
And I'll go into the next slides and explain the nitty gritty details of what they're talking about.
So this big blue one is EGS. What's that?
EGS 500 plus GWE.
But what does EGS stand for?
Enhanced Geothermal System.
Oh, that's it. So, and is this potential energy?
I'll go to the next slide.
Okay.
I'll explain
Okay,
it. You'll
it'll make
understand.
sense. Okay, all right.
Okay.
Thanks. Okay.
Okay.
Oh,
Lots of questions. I got that. I got more
okay,
slides, and I'll explain.
Okay, great.
So you can see. So that's a picture taken up in Iceland. So every 1,000 meters you drill into the Earth, the temperature increases by 25.7 degrees Celsius. Or put
I'm
another
not
way,
slide changes down.
I'm sorry.
I'm not sure this is me, but I'm still stuck on that one slide.
I see every 2,000 feet you drill.
Okay.
Yeah.
I don't know whether it was just my system wasn't catching up. Like right now, all I see is the there. Okay, now I see it. Now I see it.
Yeah, maybe it's a slow update.
Okay.
So put another way, every 2,000 feet you drill in the crust, the temperature increases by 30 degrees Fahrenheit. So the oil and gas guys know this. So the crust in North America is 43 kilometers thick. In the Pacific Ocean off the coast of Hawaii, the crust is only 6 kilometers thick. Underneath that is a sea of molten rock, an infinite power source for all practical purposes. So I'm talking about an energy source that, for whatever reason, whether you're in the green camp or you're in the I don't care about pollution camp, nobody ever talks about this right here, right in the middle, which kind of really actually blows my mind. I know the people in Hawaii, they definitely know about this, right? Because that's one of their complaints against their local public utility is, why can't we do more of this, and hopefully we can get in a more less expensive electricity.
Right. Yeah, but the indigenous are
well, like I said, most people don't realize underneath you there's a sea of molten rock that's thousands of miles thick. You just don't realize it's there. Every once in a while it pops up. I think, Andrii, you talked about that anaerobic oil, and I told you I can show you what's actually comes out of our planet. This is what comes out of our planet.
Yes.
But what Andrew's saying is we do focus on the cultural aspects, like in Hawaii. the goddess Pele is the goddess of volcanoes and lava. And so we have to take that into account when we start talking about using that resource for energy production.
And just for clarification, it's Andrii.
I'm sorry, Andrii.
That's all right. Okay, go ahead.
Okay, here we go. The next one. So I've got some good examples of some communities that actually use this type of energy. So in the 1890s, a resident of Boise's Warm Springs, that's Boise, Idaho, Warm Springs district, drilled a well and hit hot water. He started using the hot water to warm his home, for which the idea spread. Today, there are over 300 homes heated from the same set of hot water wells drilled in 1892. In 2023, a request was filed with the U.S. Department of Energy for a grant to replace the piping that was last replaced in 1973. The response from the Department of Energy was the neighborhood is too wealthy to warrant a grant. Funny thing is, driving around the neighborhood, you're more likely to see a Peterbilt or Kenworth semi-truck. These are working class people. They received a 50-year loan from the Idaho Water Board for $3 million. Total cost of heating a home in this neighborhood is about $36 per month.
Wow.
It's inexpensive.
Mm-hmm.
Okay. And I'll go to the next one. So.
And do they have winter there?
I'm sorry?
Do they have winter there?
Yes, of course they do.
Yeah. Okay. Well, because
surrounds the place. They got some world-class skiing there.
Oh, great.
After a serious energy crisis in the 1970s, the mayor of Boise took the governor of the state of Idaho down to Warm Springs Pump House and pointed out the obvious. By 1983, the several wells had been drilled and thus started the conversion of Boise to a geothermal city. Today, all of the buildings in downtown Boise, including the Capitol building, are heated with geothermal. The geothermal public utility has been converting the surrounding neighborhoods to geothermal at the request of residents. Average of $38 per month per home for heating. It's a local energy source, locally controlled, inexpensive, and safe. By taking towns off the gas grid, more resources can be made available for domestic and LNG exports. Stan, I know that New York City has basically banned the use of natural gas in buildings. I'm pretty sure they could probably, implement something like this.
Certainly could.
My understanding is that the crust is thinner in the Rockies area, or at least it's easier to get to.
It's thinner out in the Pacific Ocean off the coast of Hawaii. It's thinner in the ocean than it is on land. And the reason why is because you've got all the weight of the water sitting on the crust.
Mm-hmm. I think it was also the tectonic plates meet, like where they meet, it's thinner, where it's easier to get to.
That could be. I mean, we're going to talk about implementing geothermal. One of the places you don't implement it is actually geologically unstable locations. Where you locate geothermal assets is in geological stable locations. It's just as simple of drilling in the crust, the temperatures increase.
Mm-hmm. Okay.
So Raft River Geothermal Power Plant. Binary geothermal power plant brought online in 1980, initially produced 140 megawatts per hour. Working fluid is Pentane. Pentane supercritical at 198 degrees Celsius. At 250 degrees Celsius produces 100 bar pressure. Bought by Ormat in 2000 and converted to 20 megawatts per hour. And operation for 45 years. So the Raft River Geothermal Binary Power Plant was brought online in 1980 by my dad, Donald Gowin, and his submarine friends. The water comes out of the ground at 320 degrees. The power plant is over 100 miles from the nearest geothermal source or geologically unstable location. This all came about from a Department of Energy grant sent to the Idaho National Engineering Lab during the 1970s energy crisis. So you've got these geothermal power plants out there now that the most of the public doesn't know this even exists. Ormat converted to 20 megawatts. 20 megawatts is more than enough power to supply electricity for 12,000 houses. There isn't 12,000 houses within 100 miles of this plant.
So what do they do with the extra electricity?
Well, they just have spinning reserve. I mean, it's an infinite power source. It just uses water to run the plant.
They basically they don't have 140 megawatts worth of generation at the site now because they don't need it.
You don't have enough houses around there to.
I see. It is converted to 20 megawatts.
But it's capable. It's capable of 140, but they only use 20.
Mm-hmm. Yeah. Mm-hmm. Yeah. Okay. I thought that they'd produce
it was Westinghouse
fertilizer or something.
It was Westinghouse, and they ran it with that Westinghouse steam turbine for 20 years before Ormat bought it in 2000. So it's 1980, 2000 they ran. And understand that Westinghouse steam turbine. I talked to my dad. It was actually donated to the project from some some electric utility that had a coal-fired power plant they disassembled, and so they had this old Westinghouse steam turbine to sort of give away. So.
And so you said it's 100 kilometers from the nearest unstable.
Yeah, the nearest geothermal source is at least 100 miles from here. You got to remember this plant is probably 400 miles from the Yellowstone supervolcano.
Oh, I see. Mm-hmm.
It's in southern Idaho. It's between the border between Utah and Idaho is where it's located at.
Mm-hmm. Mm-hmm. Cool.
Okay, next one. So talk about some of the engineering here. So this is an engineering diagram. So if some of this looks like it came out of the nuclear power playbook, you'd be right. This power plant design came out of the U.S. Navy's nuclear fleet. The secondary loop after the heat exchanger is comprised of pentane, a liquid with low temperature characteristics. About 20 to 30% of gasoline is actually pentane. It's one of the things they blend together to make gasoline. The first geothermal power plants allowed live steam from the ground to drive turbines directly. The minerals dissolved in the hydrothermal water deposited on the equipment until failure. Today's geothermal binary power plants have a same capacity factor as nuclear power plants, safe, reliable baseload. So
just to clarify, the isopentane is not consumed. It's just recirculated as a fluid in a binary system.
Mm-hmm.
Right. So you inject water down in the ground. It's pressurized. It comes back up the surface. You keep it pressurized. That keeps the minerals dissolved in the water. So that's why you see the pressurizer, your injection well, your production well. And then the pentane, like I said, it goes from the vapor generator to the turbine. It's cooled down and then sent back to the vapor generator. So it never leaves the system.
And
go ahead.
The reason that you're using the isopentane instead of water or something else?
Well, because it has a lower boiling temperature than water. Water goes supercritical at I'm trying to think out what it is. At 712 degrees of Fahrenheit, and I think I'm trying to think what it is. It's like 388 degrees Celsius. The point is that's pretty high temperature.
Mm-hmm.
Versus this fluid goes supercritical, much lower temperature. You can use it to drive a turbine using much lower temperatures.
So you use supercritical vapor for driving generators?
What supercritical is, that's a state where something like steam or whatever goes into a state where it has the characteristics of a fluid, but yet it's a gas. It has characteristics of both. It's called being supercritical. It's a way of generating really high pressures for driving a turbine. Turbines turn high pressure into mechanical motion.
Mm-hmm, mm-hmm. Okay, that makes sense.
It's a technical, it's an engineering technical thing, but it's an important detail. The reason we don't use steam because it requires much higher temperatures, which means it would be much more stressful on the equipment. You'd have to drill the wells much deeper, etc.
And this pentane, that's one of the things we can produce from the syngas?
Gasoline.
Yes. Oh, okay.
One of the things, when they make gasoline, one of the things they blend in there is pentane. It's one of the things they use for making gasoline.
Mm-hmm.
So if you want to know a natural source, it'd be the horizontally direct the wells. So basically the shell oil. That's one of the sources for pentane, or crude oil. Basically, it's one of the things you refine from crude oil. The difference here is you're not burning the pentane; you're just recycling and reusing it and recycling it and keeping it.
Mm-hmm. Mm-hmm. Yeah.
Okay. So. This geothermal technology is based on horizontal drilling and fracking. Fracking had been known in the oil and gas industry since before the 1940s. The horizontal drilling had been invented in the 1950s. The primary water loop underground is pressurized for multiple reasons. One is to maintain the fracture network underground. The other is to keep the minerals dissolved in the water so that the equipment deposits are prevented. The above depicts two geothermal resources driving two pentane-driven turbines, each equal to 110 megawatts each, a total of 220 megawatts of electric power generation. Each side has two horizontally drilled injection wells and one horizontally drilled production well. So the outer tanks are the fork you see there are the injection wells. In the center, that's where the water comes back to the surface. The rock is fractured between the wells, and 8 to 10 million gallons of water is pumped in. Two geothermal reservoirs at 11,000 meters deep will maintain a temperature of approximately 282.77 degrees Celsius, which is approximately 541 degrees Fahrenheit. Only 1 to 2% of the water is cycled through the reservoirs. The steel casing is 16 inches in diameter. So understand these wells, when you drill them, that's a rather large diameter pipe that's actually going down into the ground.
And it's 11,000 meters, not feet. So that's
11,000
That's
meters.
11 kilometers. Yeah.
Yeah, that's 3 times the depth of most oil wells. And you're
Well,
drilling a 1 meter wide hole. Okay, so
yeah, well,
that's
if you're
not
in
easy.
Ohio, it's almost twice as deep as one of the shale gas wells over in Ohio. Yes, that's true. The deepest mankind has ever drilled was 40,000 feet.
Yeah.
The Russians have 16 wells drilled to that. There are 3 wells in Oklahoma drilled to that depth. There's a well in Germany drilled to that depth, and Kuwait drilled
Yeah,
a well.
but it's not trivial.
Yeah. So what temperature do you need to achieve?
Well, the temperature of the bottom here is 282 degrees Celsius.
282
That's one of the reasons why Pentane's being chosen, so you don't have to drill deep enough to make steam go critical. You just have to drill deep enough to make Pentane go critical.
Mm-hmm.
Yeah, I can also tell you what the cost is per well. It's $20 million per well.
Wow. Okay.
So it's $120 million to drill all 6 wells. So.
Mm-hmm. And would they be? I mean, for example, carbon dioxide has a much lower critical point. So why didn't they use that, for example?
You could use supercritical hydrogen, supercritical CO2 to do it, but then you have to pay much more closer attention to leaks and so forth.
Oh, okay. It's because the pentane is a larger molecule; it won't leak.
Well, remember, the pentane's only used at the power plant on the surface. It's between the heat exchanger and the turbine. What we're talking about is we're injecting water down into the ground, and basically enough water to create almost a lake or 2 lakes underground.
This seems to make so much more sense than using fossil fuels or something. Why don't we? I mean, if it only costs $20 million to drill such a well, why? How much is the electricity when you're all done from this? Why aren't we doing this?
You're absolutely right. That's why I'm showing this. If you want to know who's military, we implement this. A lot of facilities out west that most of you don't know that exist out there, and these are the type of power plants that we're building. And it's based off of work that came at it. Like I said, my dad and his Navy friends, back in 1980. So
yeah,
of course, Orma, they've got a plant there in Hawaii. Stan, I'm sorry.
Yeah, to look at it from a slightly different perspective, Charlie, is nuclear power is probably the most efficient, and we've got the best nuclear reactor in the middle of our Earth. Why are we building man-made nuclear reactors?
Yeah, and this doesn't. You can't make bombs out of this.
Correct.
Yes.
So
yes.
that's why this
Okay.
And you don't have to dispose of the fuel.
No, it's just water. You're just circulating.
Exactly.
It's just water.
And how long does it take to cool down, or does it run forever?
It never cools down. It never cools
The geysers in California are cooling down.
And that has to do with how they've structured it. If they build a thermal reservoir that's too small, you'll cool down all the rock around it. That's why I specifically told you 8 to 10 million gallons. For example, Raft River, today, the water coming out of the ground is 320 degrees Celsius. So that formula I gave you is actually conservative because the temperatures are always higher.
There's a Canadian company called Ever that does a closed loop system, which is, they call it a radiator. That one actually has a potential to lose heat over time because it's a fairly small area. But this fracking and system that Dan's talking about is a much bigger field. Like you said, 1 million gallons of water.
Yeah, you're talking about maybe 16 square kilometers underground. That this thermal reservoir, the size of it, it's huge.
It tends to not deplete the heat as quickly as a small radiator type geothermal.
So basically, it'll get replenished by geothermal energy.
Right. Well, remember, only 1 to 2% of the water cycled through the reservoirs. For 98% of the water stays in the reservoir collecting heat.
I see.
Yeah, and water has really great thermal characteristics to it.
Yeah, it does.
Yep. Okay, so we're going to talk about the operational, whether you're going to put it on the power grid or not going to put it in the power grid, and that'll go back to the cost that you're talking about, Charlie. And I actually have some charts from the Department of Energy that'll get in the nitty-gritty details of cost and so forth. So the following is a turbine designed for load following on the power grid. When attached to the power grid, you're always balancing the load to the generation. If there's not enough generation on the power grid, you will get frequency drag. If you're generating more power than necessary, you're wasting fuel. Looking to the left of the generator on this diagram is the turbine. There are 5 bleed-off valves attached to the turbine that recirculate steam back to the boiler. This maintains the temperature and allows less fuel to be used. So if you have generating capacity assets on the power grid, right, you're always basically balancing fuel to your frequency, maintaining frequency, and only burning as much fuel as necessary. So that's true with gas, coal, nuclear, and of course they also have biomass plants out there also. The only power plant out there that's attached to the infinite power source happens to be the geothermal power plant.
Mm-hmm. And it's
Okay.
much more stable than other renewables.
Well, we'll get to that. It's base load.
Okay.
This has the same capacity factor as nuclear power. I've got a chart. I'll talk to that. Okay.
Mm-hmm.
Okay. So we'll go to the next one here. So notice a little change in the diagram there. So this might be a better option considering the brass paradox, removing towns off the power grid to make energy more resilient. Since a geothermal power plant is attached to an infinite power source, removing all the bleed-off valves will allow for full power operation. There will be less wear and tear on the turbine. This power plant would have a lot of spinning reserve, a full power 110 megawatts, whether the town was using the power or not. Not on the power grid. Adjusted for inflation, the CapEx maintenance and operation will be $6 per megawatt hour, amortized over 50 years. So if your town decides I want to disconnect for the power grid and hook this up to like your substation, understand your employees and your maintenance. Your employees would be your employees. You got the capital expense when you originally built the plant. When you originally built the plant, that's where most of your capex is, which is actually drilling the wells. These plants are actually more viable used than they are new. And of course, like I said, the operations, that would all be basically the mayor of your town would be how you
yeah.
implement.
So from what I'm hearing, this is actually cheaper than nuclear.
Yeah. It also goes back. Remember the old town gas system where Baltimore made their own gas or Honolulu made their own gas. This basically goes back to that time. When you're not attached to the power grid, you've got a lot of freedom to optimize your power plant is what it boils down to.
Yeah, there's another slide coming up that talks about capacity factor, return on investment that compares all that. So you'll see that.
We'll get that.
Okay, cool. Mm-hmm.
So I got a picture in there to show you what it actually looks like. So at 110 megawatts, a turbine, the blades are made from stainless steel. The rust is caused by steam. If Pentane was used, the blades would be nice and shiny. Once every 10 years, these guys show up and basically crack the casing of your turbine and rebuild it. Now, for example, that one's there's got a blade over there and it needs to be replaced. The reason why I point this out, especially for a mirror, you don't have to have expertise for knowing how to run one of these machines. If your people know how to turn a switch on or off, that's all they really need to know. If it makes some funny noise, call someone. The point being is like I said, these guys travel around doing maintenance on these turbines. So it's a low maintenance power source is what I'm getting at.
And so are you saying that with Pentane, you wouldn't need as much maintenance?
Well, with Pentane, more likely you'd have less maintenance because the steam is actually what causes those blades to rust. If you use Pentane, that would be taken away. They actually last longer when you use Pentane instead of steam. Steam's corrosive. There's oxygen that gets dissolved in steam, and that's why it's so corrosive. So even after 10 years, like I said, it looks like it's corroded. That's what it is. Okay, so here's that chart from the Department of Energy that will make everybody happy. So the left column is the capacity factor of a given power grid energy source. The far right column is the inflation adjusted price per megawatt hour coming online in 2040. So that shows you how much inflation the government's projecting. Geothermal is the least expensive baseload we have as per the U.S. Department of Energy. The second most affordable power source is home solar panels. Renewable energy is delivered directly to your home. In this chart is a hidden secret, a knockout combination. So on the left-hand column is your capacity factor, and you see the geothermal has the same capacity factor as the nuclear power, but yet when you look at the costs, that's actually the least expensive baseload that we have, and the only other energy source that even competes with it is standalone solar in your $1.07 per megawatt hour. But remember, the solar in your house is only about 90% of the time. So,
solar has the unreliable, and then also it takes up a lot of space. If you were trying to do like megawatts.
Yeah. Well, this power plant you can fit it in a Walmart parking lot. That's how small a geothermal power plant is.
Wow.
Yeah, where standalone solar works best is if you're an isolated community, because all the distribution of electricity is really what costs a lot. You know, when you look at your electric bill, some electric companies break out distribution from generation,
Mhm.
but the distribution costs. So if you have solar on your house and you're a couple miles away from town, it makes sense to put solar on. It's inexpensive, and it gives you, it only the capacity factor is only 30%, but hey, you got batteries, and that's why it makes sense if you have solar on your house, you have battery system, because at night you need to have the batteries to back up your power. So, it makes sense. It's as cheap as geothermal on an individual household scale, and it makes sense because you don't have all the distribution costs that a grid has.
Mhm. Mhm. Wow. Well, that's
Okay.
amazing.
Any questions so far? Like I said, this geothermal it's showing here, that's geothermal attached to the power grid. There are a lot of things that because you manage your energy source relative to the grid and what the grid requires your energy source provides. So that drives a lot of your costs. If you can remove the power grid out of the equation, your costs drop dramatically.
I guess my main question is like, what's the catch? Because it's just so good. Because I know Westinghouse Nuclear, they're doing this. They recently did a contract for the small
Well,
modular nuclear reactor. It was 100 million, which
well,
is a lot
here's
more.
the catch. Here's the catch. And
Mhm.
just right there in this chart is nuclear is expensive, right?
Yeah.
The other thing
I,
is when I give
I
you an
mean,
example, when they talk about
Mhm.
small modular nuclear, the nuclear fuel is $24,536 per kilogram. So
Mhm.
the reason why you never hear about something like this is because, let's say, for example, I started up a geothermal power plant in Georgia. That power
Mhm.
plant's going to be in competition with a $36 billion 2 gigawatt nuclear power plant. So basically, we have a lot of systems out there that are financed, right? And there's a massive amount of capital that took to build these systems. And when something like this shows up, I understand a geothermal power plant when you're talking about the environmental impacts and how much time it takes to build one, it only takes you about 2 years to build one of these. If you're talking about a coal-fired power
Wow.
plant, it'll take you 7 years to build it. And Vogel out there in Georgia was 16 years. So yeah, the catch is you've got all this capital expenses already in place, right? And the problem is you have those that are managing the money will have a hard time explaining, why did I spend $36 billion on this? On this 2 gigawatt, two Westinghouse AP1000 reactors. So there's the catch.
I see. Yeah. Well, I meant, what's the catch with the geothermal? but I guess that's what you're
I
saying.
don't know. I mean, we've been
Yeah.
running Raft River for 45 years.
Hmm. Hmm. Okay.
I don't know.
Wow.
Don't
It
know what
seems
it is.
like the most viable
It also is,
transition.
notice they never advertise it. So the good stuff they never receives advertising.
Hmm. Hmm.
It's just like Boise being geothermal. You never hear about that. It's
Yeah,
never
that's
talked about
true.
anywhere.
Hmm.
But the community will never go back to natural gas.
Well, if you knew about geothermal, you'd probably never do nuclear power, at least not
Yeah.
at this scale. And
Yeah.
and so it's a lot of it's just marketing. Somebody had a great idea to do nuclear power. The Navy uses it for submarines and aircraft carriers. That's great, but
Hmm.
they can afford it. And so the technology is great. They talked some municipality into putting in a nuclear power plant, and nobody ever talked about the geothermal power plant could be a lot more cost effective.
Yeah. It's less than half the price.
Yeah, I
And
try to
a lot safer for humanity or the
Yeah.
rest of the
Yeah,
world.
a lot safer all the way around. I try to
Hmm.
explain to people because my family, my family's nuclear Navy. Like you're talking about a propulsion system for a weapon system. The costs are irrelevant. It's a weapon system, right? But if you're trying to use it to make electricity, you're not going to get cheap electricity. I mean, you can see the prices there. It's $80.2 per megawatt hour. It's expensive. It's expensive electricity.
Yeah, there's even a theory out there that the reason we went nuclear was so that the military would have enough uranium to and other fissile material to make nuclear weapons. So
Yes.
that's what
Yes.
Dan's talking about.
Hmm. Hmm. So, is this your last slide, Dan?
No, I got
No.
another one. Here we go.
Okay.
Next
Okay.
one.
Hmm.
Now, understand I talk about things the military doing that the public doesn't know
Hmm.
exists. So the PEM electrolysis, invented in 1959 by General Electric. The PEM electrolyzer turns water and electricity into hydrogen and oxygen. The U.S. Navy uses it to convert seawater into oxygen on board nuclear-powered submarines. Originally called the polymer exchange membrane electrolyzer, today we call it the proton exchange membrane electrolyzer. What passes through the membrane is a proton. It's truly a quantum device. In one format, this device turns electricity and water into hydrogen and oxygen. In a separate format, it turns hydrogen and oxygen into electricity and water. The PEM fuel cell was born. Both devices have efficiencies in the 80 to 90% area. So the reason why I say that is because you have people that are, we have chemists out there will sit there and say, well, Dan, you're violating the laws of thermodynamics. And I have to remind them, well, first of all, this is not a chemical device. This is a quantum device. It actually has much more in common with like field effect transistors and so forth. The other thing, that I talk about too, when people talk about fuel cells and they push back on fuel cells, they talk about something about platinum or it's too expensive. Well, understand, I've got in my hand, I can't show the screen. I've got a 1 ounce platinum coin minted by the Australian government. It's got a platinum kangaroo. This coin has 22 grams of platinum in it, right? The Toyota Mirai fuel cell in the Toyota Mirai car contains.
Hold it in front of the camera.
Platinum. I'm sorry?
Hold it in front of the camera. I can't see it. Oh. Okay. What is it?
It's a platinum kangaroo. Coin. It's a 1 ounce platinum coin minted by the Australian government. Yeah, it contains 22 grams of platinum. The Toyota Mirai car has 20 grams of platinum. I'm trying to tell you there's more platinum in this coin than the Toyota Mirai car.
So how much is that coin?
It's $1,100.
Oh, okay.
I bought it online. So, next. Fuel cell powered torpedoes. The U.S. Navy found a use for that hydrogen byproduct, a submarine power.
Okay, excuse me. I got to go, but I want to ask one question.
Sure.
Okay.
I got to go now. You see, I'm sunburned. So my wife is, we got to go hike or whatever. And so my question is this. I've always been concerned about the environmental impact at the other end of the wires. Not just the making it, and I apologize, they're mowing the lawn at this park, but so there's a lot of background noise. But the question I have is, all of this is marvelous. The trouble is I don't see any end to it. And so that, if you're right, then humanity could expand upon the Earth's biosphere indefinitely. And that's what...
No, that's not why I'm saying, Charlie. You get all the way to the end. All I'm saying is the economy will devolve back into the village or the city-state, right? And I'm just pointing out, basically, we're going to go back to that economic model of Baltimore, the city-state, basically being able to provide its own power and its own services is what's going to happen. That's all I'm pointing out. I'm not coming up with a solution to keep maintaining our globalized economic system. I'm not quite sure how to do that without using diesel or something like that for powering the big ship.
Well, you can make all the diesel you want. You showed us that earlier.
I don't think so. I don't. We only produce enough biomass to produce about 2 million barrels a day, and if we use trash, maybe 6 million barrels a day. We're never going to.
Well, I'd like you to think then about what will constrain this. This is a brilliant talk. It really, really interesting. And all I ask you to do is think a little bit more about the other end of the wires.
Right.
Charlie, to your point, most of the Western countries in the world are actually depopulating, not increasing population at this point. So I think it goes back into the brass paradox that Dan talks about. It just because you have more resources doesn't mean you're gonna overpopulate the earth and run out of food.
I'm not sure, but okay. Stan, do you know Richard Ha?
Yes, I do.
Say hello to him for me, please. Okay, bye.
He's the best farmer around.
Dan, that was a wonderful talk. Very, very interesting. The historical perspective, especially to me.
Right.
Bye.
Okay, no problem. Thank you, sir.
Yeah. Well, I just wanted to add that with using the electrolysis, you could make hydrogen, and then you could also, say, extract carbon dioxide from the air, and then you could make diesel. I mean, if you have unlimited energy, you could do anything.
Well, you could do that, but let me go in with the presentation. I'm not sure.
Sure.
We have to basically, you can make any diesel fuel. I mean, there's a lot of things we've already done. For example, you've got these fuel cell powered torpedoes that the United States Navy uses. These these drones that we're using today. Let me go to the next stage here.
Mhm.
So this drone here is it's a ladies flying torpedo drone. You can stay aloft for 3 weeks on a fuel cell, hydrogen, air, and an induction motor. So once this thing, you fire like a torpedo, breaks the surface of the water, and it flies around. So the United States military, we're using a lot more drones than we are using like fighter jets and so forth. We're using a lot more space technology in our warfare. For example, in the Ukraine war, it's pretty much ground to a halt. We're back to World War I because of the drone technology. So, okay. Let me go to the next one here. So when I talk about not using diesel, I'm not sure we really have to use diesel. Hydrogen fuel cell powered vehicles in the upper left of the 2017 Toyota Mirai fuel cell vehicle. Understand that's a vehicle you can buy today. It's produced by Toyota. You can actually order it and purchase it. The top middle depicts the partnership with Kenworth and Toyota, a drop-in fuel cell kit for Kenworth Class 8 trucks. So if your semi-truck starts burning oil, you go down to your Kenworth shop. They got to have an overhead crane. They pick it up. They pull at your transmission, diesel, and replace it with a fuel cell with induction motors. Upper right corner is Hyundai's panel truck. Middle left is the Colorado ZH2. The military has done extensive testing with this vehicle. Fuel cells turn 80-90% of chemical energy into electricity. This vehicle has very little thermal signature. The U.S. military uses ultraviolet and FLIR cameras to measure the amount of CO2 our enemy's vehicles belch out. It's one of the ways we track basically radar absorbent airplanes. The middle bottom vehicle is the GM Surus. It's a robot truck named after Hannibal's war elephant. This vehicle looks like a skateboard. Surus is a robot truck with a 200 kilowatt fuel cell. PlayStation control with a USB port can be used to control Surus. Surus came out of the autonomous ammunition handler program, so the robot will follow another robot. The right middle image is some of the JCB's heavy equipment. Lord Bamford's family company there in England. JCB was founded in 1850. Originally, they made water pumps powered by Syngas. Today, hydrogen-powered diesels bring this family-owned company back to its roots. The bottom left image is a Surus carrying a 40-foot cargo container. The bottom right image is the Toyota Hilux, a four-wheel drive hydrogen fuel cell truck for the inner child and all of us. So I'm not sure we have to make diesel fuel when I can just use the hydrogen directly under high pressure. And I'm going to go through some of the high pressure systems.
Just the high point as Dan changes, the trucks are the place where hydrogen makes the most sense. Long haul transportation with electric vehicles, pure electric vehicles and batteries just isn't going to hack it. If you put enough batteries to go 1,000 miles on a truck, it would weigh so much that you couldn't carry any cargo and you'd be tearing up your roads. So hydrogen makes so much more sense. Going back again to Dan's first slide about energy density.
Yeah, so, the Colorado ZH2 has a PTO on the back of it. It's got an inverter. You can pull 220, 440 off the back of that vehicle. That's the reason why we're interested in it, because that way we don't have to drag around generators and so forth. For example, the Air Force, they want to use this at Air Force bases to use it to start up fighter jets.
Wow.
But yeah, it's almost an invisible truck. You can't see it with thermal imaging cameras.
Oh, that's the SUV over there?
Yeah, on the left-hand side. It's based off the Colorado.
And so how many kilometers do you get from a fuel cell truck? Like
that's a good question, and we're going to go into that, okay?
Oh, okay, sure.
Yeah, the next slides basically go into what you're talking about. Okay, so we're going to go to the next one here. So this car here, this is called the Koenigsegg Gemera. It's a sports car. It's the fastest car in the world. It uses 4 Quark radial induction motors, one behind each tire with a disc brake, 0 to 60 miles per hour in 1.9 seconds. Top speed is 325 miles per hour. It's a hybrid electric car powered by a 3-cylinder internal combustion engine, driving a 3-phase 500 kilowatt generator. The system uses ultracapacitors for a buffer. The engine can use nitromethane, DME, or hydrogen as a fuel. The model shown has a capability of producing 1,340 horsepower. Stan, they've got that new model that does 2,000 horsepower, but that radial induction motor you see right there, it's about the size of a watermelon. They weigh about 63 pounds each. Induction motors, you can go from 0 to 100,000 RPM. So this car doesn't need a transmission.
So look up Hyperion when we're done here, and you can see another nice car.
Yeah, you'll find out just cars in the world are these type of.
So could it outpace a Tesla, or I don't know?
325 miles per hour.
Okay,
it does 0 to 60 in 1.9 seconds. Yes,
because it's lighter.
I'll go back to the page. I'll say. 0 to 60, 1.9 seconds. Max speed, 325 miles per hour. That will smoke your Tesla easily. That will smoke most Formula One cars, right there.
Wow. Okay.
Yeah.
Cool.
Yeah.
Because I know
That's what makes the
I've just
fastest
been
car in the
seeing
world.
those videos of like the Teslas beating Ferraris and stuff.
Yeah, and it doesn't weigh as much as your Tesla because it has no batteries.
So notice the foil on the front and the back. That's to keep it on the ground because it doesn't have the weight.
Yeah, it'll fly right off the ground.
Oh wow!
If you don't have that on there, yeah. So we'll go to the next one here. So yeah, I had this added in there for actually Simon. So it's from Hydrotech, that's part of General Motors up there near Detroit. They've got a collaboration with Komatsu, and they're converting these mining trucks over to hydrogen fuel cell. So, and if you want to know why they're doing it, because they're trying to get away from using diesel or gasoline as a fuel. It's a business decision. It's not based off of philosophy or polluting the environment. It's just a practical business decision of why they're doing this.
So I'll throw some data in here for you, Dan. If you take a gallon of gasoline and compare it to a kilogram of hydrogen, you can go 2.6 times the distance on a kilogram of hydrogen as a gallon of gasoline in a similar vehicle. That helps you do the calculation.
Well, the other thing is an internal combustion engine. Hydrogen burns faster, so your engine will rev up to much higher RPMs because it burns quicker. So it's a much higher energy fuel energy.
So I have a YouTube question here. Hydrogen requires exotic allies to contain and transport it, doesn't it? And then there's also the fuel cell waiter. That's the question.
A lot of questions there. I'll answer them if you let me go forward.
Oh, okay. Ivor has a question before we go on. Go ahead, Ivor.
Well, gasoline is the thing that burns in gasoline is the hydrogen. And what percentage of gasoline is hydrogen anyway? Is it like 50, 60%?
I don't know. I'd have to research it, but it's hydrogen attached to carbon atoms. It makes a nice convenient fluid in a container. It's very convenient.
Yeah. So I mean, it's powerful. Also, I mean, you think about it.
It is, but when you look at it per kilogram, the hydrogen by itself in a carbon fiber tank has higher energy content than the gasoline does. That was the first slide we showed. And gasoline is 18,700 BTUs per pound versus hydrogen is 51,000 BTUs per pound. So a pound of pure hydrogen has 2.6 times more energy in it compared to gasoline.
Okay.
Worth noting, though, that you can burn hydrogen in an internal combustion engine, but if you want to be more efficient, because internal combustion engines make a lot of heat, you put it in a fuel cell, and the fuel cell is where you get the fuel economy in a vehicle, because it turns a electric vehicle into running on a fuel rather than just hauling batteries around.
Yeah.
So you have hydrogen tanks in a fuel cell vehicle, and the weight is way down. And your electricity production, and you can't get better torque and stuff than you get with electric motors. So the whole system's together. When you take it from a systems level, hydrogen is much more efficient than internal combustion, and it's much more efficient than electric vehicles and batteries because of the weight factor.
Mm-hmm.
Consider all locomotive trains you've ever seen that is a hybrid electric vehicle. There's no transmission in there. The bottom carriage, there are either 4 or 6 induction motors. Each induction motor is 4,500 horsepower. It's about the size of a V8 engine block of the induction motor. Up in the cab is a diesel generator. That's why it's easy to convert trains over to all electric or even hydrogen, is because those are hybrid electric vehicles. So the engineers we're basically focusing on the induction motors, the efficiency of them. And an internal combustion engine, the efficiency is 20%, diesels are 40%. When you talk about fuel cells, it's in the 80 to 90% efficiency.
Wow. Yeah. The one interesting thing about trains, though, is that's one place where weight, in an inverse reason, doesn't make a difference. Your train engine has to be heavy enough to keep traction on the tracks to pull a long train. So you want to have as much weight as you can in the engine so it can keep traction.
Otherwise, you could use ballast of some kind.
Yeah, exactly. And that's all you need.
Yeah, if you pulled out the diesel engine, you got to put a big piece of steel in there just to make sure you got
just
enough
to
weight.
keep it. Yeah.
And
Or I guess
you got 4 induction motors. Add that up, that's 18,000 horsepower, and then 6 induction motors, that's 27,000 horsepower. There's no way to build engines that scale with diesel. There's just not possible to do it.
And so I'm guessing could do boats too, right?
I'm sorry?
Could have boat engines.
Yes, you can.
Yeah,
look
we
up
do.
look up zero emission industries, and you'll see boats. They made a hydrogen ferry in San Francisco.
Yeah.
Oh, great.
And that's just
to give you an example, my favorite is the LM6000 gas turbine. We used the LM25, 2 of them inside of an Arleigh-Burke-class destroyer. That is a hybrid electric destroyer. So all our ships, submarines, are all hybrid electric. We use a nuclear reactor, drives a steam turbine generator, drives an induction motor that drives a propeller. So we do it for efficiency. Okay, next one here. So when it comes to storing that gas in tanks, at least for the vehicles I've been showing you, so it's a Type 4 tank shown above, was developed in 2000. Top pressure in the Turbines fuel tank is 700 bar. That's 10,000 psi. And yes, it's 25 years old. So that is made out of some really common materials for holding the hydrogen. The inside liner has high density polyethylene plastic. That aluminum thing down at the end, that's 775 aluminum for the what we call the boss, and then that's carbon fiber wrapped around to make that tank. These tanks are becoming pretty ubiquitous. That bottom right hand, that's actually a tank for a paintball gun, because you can pressurize a paintball gun tank up to 4,500 psi.
So this is what you use for storing hydrogen. And those,
the Turbines car, that's where you store the hydrogen, is in these tanks.
Mm-hmm, mm-hmm.
So it's not a special material. It's pretty common kind of stuff.
And because you have limited space in especially a passenger vehicle, Turbines has like 4 tanks. They're all small and they fit in different places, but they can be pressurized to 10,000 psi.
Okay. And then how much hydrogen would you be able to store in that?
The Mirai has about 5.5 kilograms of hydrogen.
5.5 kilograms. Well,
and we got a chart for that.
Yeah, we've got a chart. We'll talk about the pressure and basically how to use different pressures and store even more gas in there. But 5.6 kilograms of hydrogen in that tank in the Turbines car, according to the Department of Transportation, the mileage is 402 miles on a fill up. So I think I get like 350 out of my truck. That's actually pretty good.
And the record with a Toyota is 845 miles on a fill up.
Guinness Book of Records, yeah. So that's the next one here. So for the longest time, we knew what materials were impervious to hydrogen and impervious to hydrogen embrittlement. A lot of people talking about embrittlement, which anyway, in 2010, Fermi National Labs, in collaboration with Eli Lilly, figured out the mystery. The above image is an X-ray diffraction of 316 austenitic stainless steel. All the atoms are connected in triangles, not enough space for a hydrogen molecule for intercalate between crystalline layers. No way for Brownian motion to destroy atomic bonds. All the materials listed above are impervious to hydrogen. Imagine, if you will, you're at the beach, and I'm going to try to explain this. So let's try to explain what embrittlement is and some of the issues with the molecule and the size and so forth. The easiest way to describe this is, let's imagine you're at the beach and you're going to build a retaining wall and you're going to use bowling balls, and you attach the bowling balls together with screws or epoxy or something like that. And you start shoveling the sand behind this wall, and you say, Dan, that's not going to work because the sand leaks in between the bowling balls. And I say, that's exactly the problem. The bowling balls are the iron atoms and the sand happens to be the hydrogen atoms. How you solve this in stainless steel is you add nickel and chromium to it, and the nickel and chromium actually fit in between the spaces between the iron atoms. And so that's why you can use stainless steel, 303, 306, and 316 in stainless steel that are impervious to hydrogen. One of the first materials that was discovered, I think, back in 1736 was that copper, brass, and bronze are impervious to hydrogen. It doesn't affect it. Obviously, NASA knew something about it because back during the Apollo era, they developed all these copper alloys for liquid-fueled rocket engines. So they obviously knew that there were materials that hydrogen wouldn't affect. Pretty much when everybody talks about hydrogen embrittlement, you're probably really talking about, yes, hydrogen destroys iron pipe. and it's iron pipe's really a low quality material. Aluminum 775, those materials are impervious to hydrogen, and your plastics, your polycarbonates, and your high density polyethylene plastics. And if you want to know what all these materials have in common, it's actually the triangles that you see. When you look at them, when you look at how the atoms are actually hooked together in triangles, there's no way for hydrogen to intercalate into the crystalline structure and basically break it up from inside.
So in short, there's a lot of people that say hydrogen is in brittle steel, so it's therefore not efficient. We couldn't use gas pipelines to transmit it and transport it in a long distance. That's not true. There's a lot of ways you can line the pipes. You can just use stainless steel. We use stainless steel swage lock fittings and stuff in all of our electrolyzers and things like that we use for our vehicles at HCAT.
The Baltimore Gas Light Company, they're in 1817. What they used, they took iron pipe and they put brass sleeves inside the pipe and they would pressure fit it, and that's how they made a pipeline for that city that was impervious to the town gas. So I'm trying to tell you that people bring up this subject about the embrittlement, not realizing you realize this problem was solved 2 centuries ago.
Mm-hmm.
Okay.
Cool. And then, well, I have a question here. Have they done any crash tests involving vehicles running hydrogen, and how have they fared?
Well, that's not true. You at Baltimore Gas Light Company, they provide hydrogen to an entire city back in 1817.
No,
I've got a better one for you, Andrii.
Yeah.
The Army has tested these tanks, these Type 4 tanks,
mm-hmm.
by shooting high-powered 50 caliber and 30 caliber weapons at it to try and make them explode like a normal tank would. If you caused a leak in it, it would turn into a hand grenade. And they were totally disappointed and somewhat amused to find out that they couldn't make a hydrogen tank pressurized at 10,000 psi blow up, because they'd shoot at it and it'd punch a hole in it and the gas would escape. Finally, they used high explosive incendiary ammunition. It punched a hole in and made a blowtorch out of the back end, but they could not get the tanks to blow up.
The other aspect about that too, Stan, is that when you shoot the tank, it's got to be exactly square. One of the things I can talk about that's been declassified is back in the 90s at Crane, we were testing carbon fiber tanks, and we were using a Ma-Deuce Browning 50 caliber machine gun with high explosive incendiary rounds. And if you're not exactly square, what happens is the rounds actually ricochet off the tank. We took all these high speed videos, and the tank with the carbon fiber will actually flex like that, and the round just ricochets right off. So if you're going to shoot one of these tanks with a firearm, you got to be exactly square. Otherwise, the bullets just ricochet right off the tank. The carbon fiber has a lot in common with Kevlar. It disperses the energy.
Mm-hmm.
So chances are, if you had these tanks in a car and you had an accident, you'd probably rupture a fitting and have it, and it would leak. And by the way, this gets in a whole nother discussion about hydrogen's, burning. And burning hydrogen, remember, it's hard to ignite when it's under pressure, but if it does ignite, the flame is very directional. And because it has no carbon in it, there's no heat radiation from the side. So what we teach the firemen in Hawaii, because we were running hydrogen cars for the Air Force, is to carry a regular broom, an old-fashioned straw broom. And because in the daylight, you can't see the hydrogen flame if it's burning. And just the firemen would just stick a broom out in front of them as they're walking. And if the broom caught on fire, they knew there was a flame there. And then they basically let the fire burn out, because the flame is so directional. If there's nothing in the way of the flame to catch on fire, they just let the fire burn out. So it's a whole different philosophy in fighting hydrogen fires in vehicles and things like that. But it's been well studied.
They had a similar problem with the old town gas system, actually, because the flame is actually kind of a deep blue when it burns the town gas. So what they did, when I'll show you the last slide, has actually a gas lantern, and they use those old mantles, and the mantles actually glow from the burning the hydrogen, because when you burn hydrogen, it emits UV light. So understand that some of the stuff we're talking about burning hydrogen, for example, when you got hydrogen in a tank and you release the pressure and the gas expands, it gets cold hydrogen doesn't burn. It's really difficult to ignite this gas. And remember, it's lighter than air. It just goes straight up.
Mm-hmm. Ivor has a question. Go ahead, Ivor.
Well, this might sound like a dumb question, but now you fill the fuel cell with those with your tanks you're talking about, right? And then does it actually burn the hydrogen, or does the hydrogen get used some other way, and then it goes to hub motors, right, to move the vehicles?
Right.
What happens in the fuel cell? The proton exchange membrane literally pulls the proton right through the membrane, takes the proton, matches up with an oxygen atom, and turns into water. What
Okay.
comes
What
out of
happens?
the tailpipe of the vehicle is just steam.
So it
What
makes
happens?
pure
In a,
electricity.
yeah, in a fuel cell, what happens is the hydrogen meets up with the oxygen, but the electron can't go through that membrane, so it goes through a wire, which gives you an electric circuit, which
Oh.
drives a motor. So that's
Mhm.
why it's much more efficient than burning hydrogen in an internal combustion engine, is because it doesn't have all that heat. The only byproduct or the only products from a fuel cell are water, heat, and electricity. So you have no problems with pollution, or even you don't even have problems with NOx or anything like that, like you would burning hydrogen at a high temperature in an engine. But it's a really cool thing. I've been working with hydrogen for almost 20 years, and it's really amazing.
Yeah, you've got a high energy fuel with a really high efficiency system. The fuel cells are really efficient, and the induction motor is even more efficient.
Oh, that's great.
80-90% of your chemical energy is turned into electricity. It doesn't turn into heat. That's the reason why the military were very interested in using this for vehicles. Is the reason why.
Yeah, typical internal combustion engine is only 20 to 25% efficient. And you know that because of how much heat you have to get rid of with your radiator and everything, because
Yep.
most of the energy you're doing is creating heat, not creating traction at your wheels.
And that shows up on our FLIR cameras. That's how we're able to target you from space, basically. It's because you're belching out heat and all kinds of carbon dioxide.
So we built an electric car, and it was unbelievable how inexpensive it was. We said you could drive it around. It has solar backup also. You could drive it around in the money you could find in the parking lot, literally, the cost to do it. It was unbelievable. And that was probably, like with hub motors and things. Oh my God, you're getting more.
And that's the other thing we're looking at. There's just plain fewer parts, fewer things to break down. If you have one of these induction motors breaks down, you unplug it, you unbolt it, you send it back to the factory, get it rebuilt, you plug in the new one. It's no different than like an alternator or a starter. And that's what the military, it's just fewer parts, less to maintain. It's a simpler system.
So the Toyota Mirai is basically, and the Hyundais and all those, even Honda's building a CRV in hydrogen fuel cell hybrid. And what happens is you have a traction motor, a small traction motor, much smaller than a Tesla battery, rather, traction battery. And then you have a 12-volt battery to run your electronics, your dashboard and stuff like that, like a regular car. So your weight is greatly reduced, and that fuel cell produces all of the electricity on the fly with hydrogen rather than with big, heavy batteries. So the advantage to a hybrid fuel cell vehicle is less weight, because you don't have all the batteries. You just have a small battery, small traction battery, and the hydrogen's generating electricity all the time when you need it. When you don't need it, it doesn't generate any electricity. It just shuts off.
Okay. So if this one's controversial, the next one will be that much more so.
Yeah, and so just to clarify about this image that we're seeing here, is this? Oh, what is it exactly again?
It's an X-ray diffraction. What we did was when I was at Lilly had remember that old town gas system that Lilly had been using, and about every 20 years they're replacing pipes. So they wanted to know what was actually causing this, what was causing the embrittlement, why wasn't the copper affected, but high carbon steel was. So what Lilly did is they have a relationship with Fermi National Labs up in Chicago, and they got a synchrotron, a big atom smasher up there. And so we took these plastic tackle boxes and put all these samples in there. We used hydrogen to destroy stuff. We used stuff that wasn't destroyed. All these materials we knew that were impervious to hydrogen. The National Institute of Standards and Technology, they have a library of all these materials that are impervious to hydrogen. So we set it up to Fermi, and basically they create what's called an X-ray diffraction. They basically smash like mercury that generates gamma rays and X-rays, and they pass through the atoms themselves, and it creates a shadow. And what you're looking at is the shadow of the actual atoms. What Lilly uses it for, they use it for figuring out drugs. We have the computers model what a drug looks like. We send the samples up to Fermi. They actually model, actually show us what do the molecules actually look like, so it doesn't match our model. So we did the same thing with all these materials and figured out that why these things are impervious to hydrogen had to do with the triangles. All the atoms are connected together in triangles. There's not enough space between these atoms for the hydrogen to intercalate between them, and by Brownian motion is a molecule vibrating, can break atomic bonds. So it doesn't affect these materials because of how they're structured at the atomic level.
And what specific material are we looking at?
Well, you got your stainless steels. It's a 303, 306.
So all of them would look like this?
Yeah, when you look them at the atomic level, they look like triangles.
Okay.
And they form this Star of David pattern.
Uh-huh. So all of these materials would form the same pattern, basically?
Yes.
Okay, interesting.
Yeah.
Okay.
Yeah, that's what they all have in common. They all is like, when you look at one at a time, it's like, is this the picture of the same thing? No, it's a different substance, but you get the same pattern of triangles. Okay.
Cool.
Okay, so this is a company called High Pressure Equipment Incorporated. They've been in business since 1960. Most of their customers are the military. They make a variety of high pressure hydrogen equipment upon demand. So if you take a good look at that valve there, it's made out of 316 stainless steel, and it's ASME certified for hydrogen up to 150,000 PSI.
150,000. A scuba tank is 2,500.
So the tanks you were talking about before, that was 1,100 PSI? Or, sorry,
well, that Type 4 tank I was showing you was 700 bar, which is 10,000 PSI. But we're going to talk about much higher pressures and why we are following this path down higher pressures. But the reason why we're pointing this out, because you've got a lot of people out there, they'll talk about, the embrittlement thing, or they'll talk about the size of the molecule, or they'll talk about you can't do higher pressures, or they'll talk about you can't store this stuff. And so what I'm here showing you is actually real things that sort of dispel what they're saying. You know, this is one of the companies, they make material, and you can go look them up on the internet, and you can actually order this equipment and they'll send it to you. Of course, the bigger question you've got to figure out is who's got the compressor that actually goes this high. But that's and I'll show you why.
So this is for these are hydrogen regulators that we're looking at here.
There's a regulator. They got valves. They've got pipes, connectors, anything for high pressure hydrogen, and they can also manufacture equipment also. Some of this equipment you've got right here is actually small stuff, but they also build much larger stuff. I have them custom build me stuff all the time.
And so do they also have storage units?
Well, there's a number of us that make the carbon fiber tanks, like my friend Chris McWinney at Millennium Rand Energy. He builds carbon fiber tanks. Obviously, Toyota, they've got their own manufacturing for carbon fiber tanks. There are a number of entities out there that build carbon fiber tanks. If you're interested in the construction of carbon fiber tanks, I can probably put together some links of the companies that sell the machines that actually make the tanks.
Spin the fibers.
Yeah.
But yeah, the tanks themselves, they don't go to 100,000 PSI. These are just
well we're gonna
get there. Okay, I'm sorry. Am I getting
patient.
too far ahead? Okay, go ahead.
Go ahead. So we're gonna go to the next one here. So
yeah.
So there's a storage and compressor problem with hydrogen. It's a challenge compressing the universe's smallest molecule. Even after we've solved embrittlement, we still had problems compressing it and storing it. 1 kilogram of hydrogen at room pressure occupies 12,000 liters of volume. So 1 kilogram of hydrogen at room pressure occupies, it's equivalent to 6,000 2-liter bottles of Coca-Cola. Even the above state-of-the-art industrial compressor with 16-inch diameter piston is actually too small for the task. In addition, due to the size of the hydrogen molecule, vast quantities of the gas simply pass its compressor rings due to the Bernoulli effect. Essentially, the compressors burn themselves up, compressing the gas. The reason California service stations are down 50% of the time is due to compressor issues. The compressors at oil refineries use lubricating oil, and even still, they must be replaced every 2.5 years. The compressors at the hydrogen service stations can't use lubricating oil. It would contaminate the hydrogen being replaced in the fuel cell. The compressors at the service stations basically only last about 18 months before they basically destroy themselves. So they've got the memo. They're making the compressors out of 316 stainless steel. The valves are made out of copper, so they've got that. They've got the materials that are impervious. But the problem is the volumetrics of the gas require that this machine work itself to death trying to compress the gas. So they just wear these machines out trying to compress the gas.
I see.
Yeah, I'd say that compression is the bane of hydrogen up until down. Up until down.
Yeah. Well, if you want to know why the oil and gas guys will tell you some of this is impossible, it's because this is the only piece of machinery that they know even exists.
Okay.
The military is a different story. It kind of goes back to that high pressure company. What do they know that the guys at the refinery don't know? That's the bigger question.
Mm-hmm.
Okay. So any questions so far? Okay.
So you're going to unveil the one that works?
Yeah. We're going to go through. We're going to give you some answers here. Okay.
Oh, great.
So go here. This is from Sandy National Labs. That's part of the Department of Energy. In 2010, Sandy National Labs published this white paper among researchers detailing solutions to the hydrogen storage problem. It was declassified in 2011. So, so basically those that ask, I'll actually email them a copy of this document so they can read it themselves.
Mm-hmm. Geologic storage of hydrogen.
Yeah, it's how you do large, vast quantities storing hydrogen gas. Okay.
Underground, right? Mm-hmm.
Yeah, it's just geological storage. So if you click on it, so they detail transportation, compressor, cushion gas, and they talk about salt caverns, aquifers, depleted gas reservoirs, and hard rock. Now, oh, by the way, if you drill a well, right, and you don't find any hydrocarbons, it's called a dry well. Well, guess what? You can store hydrogen gas in that well. So the solution details the use of various underground storage techniques. Horizontally drilled and fracked wood dry wells are considered depleted gas reservoirs. So.
And what pressure are we talking about with salt caverns and aquifers and things like that?
Yeah, that's a good question. The refineries don't ever go above 3,000 PSI because those mechanical compressors can't get above 3,000 PSI. So I don't know what the maximum limit is, but the other aspect of that, Stan, is it's too close to the surface. So if you use higher pressures, you might get an ugly event. You're better off storing hydrogen like in aquifers or, like I said, or just drill a dry hole and store your hydrogen deep underground.
Mm-hmm.
Okay.
Are there particular kinds of rocks that are better or worse?
Not that I know of. Let me go to the next one, and we'll kind of drill down into that. So
the salt cavern ones are pretty popular, though.
Yeah, they use that at the refinery, but it goes back to it. Those are shallow, and like I said, the top end is because those mechanical compressors top out at 3,000 psi, and obviously somebody has the ability to compress hydrogen to much higher than that. So, just click on it. Yeah. Remember the old Perrier-K Syngas plant? The old town gas system is depicted on this map by the red triangles. The natural gas system was invented by George Westinghouse in the 1890s. Any town with population greater than 10,000 has a town gas plant. Baltimore Gas and Light Company was built in 1870, and Honolulu Gas Company was authorized by the Hawaiian legislature in 1859. Natural gas system was deployed in the U.S. in 1950. By 1966, all the town gas systems had been converted to natural gas, except Indianapolis and Honolulu. So what they partially documented was how the old town gas system, how they were storing the hydrogen, how they got around this volumetric problem. They were storing the hydrogen underground in gas wells. So basically the oil and gas guys, they kind of basically copied the same idea. Like down in Houston, they've got these salt caverns where they store the gas for the refinery. Up at the Whiting refinery up near Gary, Indiana, all they did is they drilled a well down 6,000 feet, hydraulically fractured the well. So they store the gas at 6,000 feet down underground underneath the refinery. They're at the Whiting refinery there in northern Indiana. So all they were doing is recognizing how you're going to store this stuff. Industrial quantities is you store it underground. It's actually the safest way to store any gas. If you know anything about the natural gas business, we store natural gas underground in gas wells.
Oh, wow. Mm-hmm. Cool.
It's inexpensive. It's safe. If you have giant tanks above ground, Homeland Security is going to come visit you.
Yeah. Oh, because they might blow up or something.
Yeah, because there's a tactical problem. But if you store it in a gas well, it's a safer way to store it.
Mm-hmm.
Okay.
Yep.
We'll go to the next one here because I have people ask me lots of questions about drilling wells. So,
I'm just wondering about the hard rock outcrops on that one.
Well, the truth is that's
okay.
like hard rock mining. I'm not sure why you would do that, to be quite
I
honest.
see. Okay.
It's a lot easier just to drill a well, right?
Okay.
This is from a driller's safety course, why the blowout preventer is so important. This graph depicts how it's possible to store hydrogen at gas pressures greater than 1,000 bar. That's 15,000 psi. You already have structures able to store gases as high as 1,400 bar. That's 20,000 psi. We're talking about for a cap rock and you're hitting natural gas, the pressures will jump to way above 20,000 psi. It also details the wells must be pressurized with drill mud to keep the wellbore from collapsing. Drill mud is pushed down through the drill string, through the cutting head to pick up rock chips. The mud and chips are pumped to the surface to be collected and analyzed by the geologist. When the cap rock is pierced by the cutting head, it usually bangs the drill string. Someone hits a big red button and activates the BOP, which clamps down around the drill string and holds the mud in there until the pressure can be safely released. There's some folks out there that talk about using like a klystron or something so they can drill like deep geothermal wells, right? But they obviously don't have a problem with what they're talking about, because anybody that drills wells knows that you have to have it pressurized mud because the earth will actually close around your well while you're drilling it. The other thing is when they drill through a cap rock into a natural gas deposits, like for example, here in Indiana, the pressures will jump to high as 25,000 psi when the natural gas is coming out of the ground. So I'm trying to tell you that one of the safest ways and also where you can store high pressure gases is actually underground. It's not above ground structures. It's geological storage.
Mm-hmm. So I'm wondering if in this graphic, the brown part that we're looking at, does that have some significance?
That's the drill mud. It puts it, drill string, you got that cutting here at the bottom. That's a pipe that's hollow. They pump drill mud down to the center. It goes through the cutting head and then up around the drill string back to the surface.
Okay, I see.
And then on the surface, they got this big screen. They basically all the rock chips go in there.
Oh, okay. So this is kind of like a magnified
view. He's probably
view.
Seen it. He's seen it.
Mm-hmm.
Yep.
Okay. I wasn't sure.
I'm just pointing out when these people talk about using klystrons, drawing the drill down to 40,000 feet. I'm like, time out here. You realize that wellbore is full of mud. How are you going to get your microwave tube working when it's full of pressurized mud? How does that work? It's probably not going to work. That's what I'm getting.
Mm-hmm.
Okay.
So if it's full of, so you have to take out the mud and then store it.
Well, but if you take out the mud, the earth will close around it. I mean, you drill it and then you put in casing, steel casing to keep the earth basically sealing up your hole.
Oh, I see. Okay. Now
so the mud recirculates and gets screened out. All the big debris gets screened out and it gets pumped back in under pressure to keep your cutting head from being inundated with.
Yeah, otherwise you'll never get that pipe out of there. It gets stuck in there. Yeah.
Okay. I think I understand sufficiently, anyways.
It's just I hear people doing them like, oh, how are you ever going to get all the water, the mud out of the bottom of that well? I have no idea how you're going to pump it dry. I just anyway.
Yeah. So you make the steel pipe and then you can pump it out.
Right.
Okay.
So energy source. So I've got here. So this is got a graphic from the Department of Energy and depicts MISO and SPP. So that's the computer system that I designed. And one of the things I talk about to people has to be with what's called curtailed wind power. What curtailed wind power is, we've got more power than we can use. If you want to know what it looks like at the wind farm, is you'll see some turbines spinning and some other turbines, the blades are stationary, not moving. We take the blade that's spinning, the turbine that's spinning, wind turbine, and we measure how many megawatts are coming out of it, and then we multiply it by all the ones we applied the brake on, and that's how much power we know we're curtailing, we're not using. So, for example, the SPP MISO area, we curtail, and you see the chart right there. Well, the last one was 2023. I haven't got the data for 2024 yet, but in 2023, we're curtailing 800 megawatts per hour. So 800 megawatts per hour times 24 hours times 365 is over 7 terawatts of wind every year. The wind's blowing and we're not using the power. Down in Texas, they curtail 16 terawatts of wind per hour. That's a lot of power that we're not using. Starting from Austin, going all the way to North Dakota, there's a 300 terawatt wind corridor. And as long as your turbines are 500 feet off the ground, the wind blows all the time. It never stops.
Mm-hmm.
And it's a whole nother discussion about why don't we use that power, but it's a legal discussion and I don't want to get into it right now, but
Well, yeah, well,
because
there's the whole contract and PPAs, and that's But
Oh, okay.
we can go into the next slide, and I'll talk about what we could be doing with that curtail wind power. Okay.
Okay. Mm-hmm.
Okay. So on the left here, you have a megawatt grid scale electrolyzer. On the right hand side, there's an LM6000 gas turbine, a GE LM6000 gas turbine, a 50 megawatt gas turbine. So using megawatt grid scale electrolyzer, 7 terawatts of curtailed wind power could be converted into 154,000 metric tons of hydrogen. That could be stored underground. The GE LM6000 multi-fuel 50 megawatt gas turbine would be the perfect choice for converting stored energy back into the electrical grid. So one of the pushbacks I get from people said, well, Dan, you're putting 7 terawatts to make hydrogen and gas and you're storing in the ground. I said, yeah, the positive is I can store hydrogen gas almost indefinitely. The problem with batteries for grid storage is that it's only good for about 3 months. When they say, well, Dan, you're burning in that gas turbine. Well, 7 terawatts going in. If I use gas turbines, right, I can turn it into 1.5 terawatts of power. So that's efficiency's not there. But if I use fuel cells, I can turn fuel cells into 5.6 terawatts of power. Now, you say, well, Dan, use the fuel cells. It's more efficient. Well, the problem with using fuel cells is the fuel cells would be scattered over a huge area to make a fuel cell park that would generate that much power. Versus an LM6000 gas turbine, you can fit that in the back of a semi-truck. So it's a very compact generating source that's multi-fuel. So what I'm trying to tell you is you're a lot better off using equipment like the LM6000 because it's a device that has much more capabilities than just the efficiency. But the other thing you got to remember, we're throwing away that 7 terawatts of electricity that we could be turning into 154,000 metric tons of hydrogen. And as a note,
that's really the key, Dan.
Yeah, we could use 154,000 metric tons of hydrogen to refuel 493,000 Toyota Mirai cars for a year of something we're throwing away.
Wow. Mm-hmm. Because of the power curtailment. Mm-hmm. Okay, yeah, it would be good to see the those process efficiencies that you were just talking about in a table. It would be easier than trying to imagine them.
Well, I'm not here to scientifically convince you. Yeah,
okay,
I have no idea.
I'm convinced. I'm convinced. I'm just
trying to say, depending on the power grid, depending on a lot of things, would actually show you the actual efficiency. I'm not saying this is a great way of turning hydrogen into electric power. What I'm saying is this is waste that much energy, right? There's a way of storing energy indefinitely, and one of the things we need in a power peaker units, right? Basically, when everybody's using their air conditioning in August, you could be having this giant 7 terawatt battery stored underground where you can bring that power, to bear, and use it to provide you extra electric power. And it's not a small amount of power. I mean, 1.5 terawatts. That's a pretty good chunk.
Yeah. Mm-hmm.
Considering the country consumes, what was it saying, 500 gigawatts of electric power per hour?
Yeah.
Right.
So you're talking about an amount of energy that exceeds the generating consumption of the country. I mean,
but
I have people really push back and say, well, Dan, it's not efficient. Like, you realize that it's 3 times the energy capacity of the country. You realize that, but they don't comprehend. Yeah.
Yeah, it's not efficient, but you'd be throwing away that energy otherwise.
Yeah, that's how much energy we're throwing away. That we could be solving a lot of these problems. You consume 500 gigawatts, but yet I can burn it in these gas turbines and turn it into 1.5 terawatts. And it's like, okay, the neurons aren't connecting here or something. I'm not sure.
I know this would also solve Simon Michaud's main mineral issue of not having enough battery storage minerals.
Yeah. Well, remember, 2/3 of the planet's covered by water.
Mm-hmm.
Yeah, we're going to get to the very end here, and I'm going to talk about some absurd things that are going on when you actually think about how much energy and power. And I talk about the geothermal and the wind, and when I look at this, like, okay, these people are complaining about something that doesn't exist. So let me go to the next one here. So fluidic compression. So this is my big area. So why use fluidic compression? A non-mechanical form of compression that uses the boundary between supercritical fluids to achieve an even higher pressures, molecularly tied at the quantum level. It's a form of compression that uses the laws of quantum mechanics to your advantage. So on the top there, that was a video that I did. It took me 5 months to record this video that's only 2 minutes and 30 seconds long. So I built a chamber. The fluid in there is supercritical hydrogen at 200 psi, and I go from 200 psi to 5,000 psi within what do you say? How many seconds, Stan, would you say that took?
I think it was around 15 seconds.
Yeah. So I put a tennis ball, a dog toy, a mason jar, and a bottle of Mike's Hard Cider. And within seconds go to thousands of psi. And crush things. So I did it because there's too many doubting Thomases out there. The bottom image is you've got two fluids. Above it's just regular supercritical hydrogen. The bubble you see is what's called trihydrogen. That's a substance where you have 3 hydrogen atoms sharing 2 electrons. And whenever you compress these gases into this fluidic state, they separate. They won't mix with each other. And the gases form, they'll mix. But when you compress them into these fluids, they won't mix. And so I use that fact of physics to use one fluid to compress another one.
So you're using the trifluid?
Well, the easiest way to describe it, actually, I use I have to compress it into these fluids, and then I use the energy states. For example, that trihydrogen, it's missing an electron. It's 3 atoms of hydrogen, but only using 2 electrons. So there's missing electron, right? So therefore, it's positively charged. And it has a different expansion coefficient than the other hydrogen does. So I can use one fluid to compress the other fluid.
Okay. Wow. Well, so will you did you unveil like your method here for fluidic compression, or is there some way?
I'm going to go to the next slide to say, okay, why we're looking at this, or why we've already done this, and then that'll probably explain a lot of the questions.
Okay, sounds good.
So understand, I built a video because in our space that Stan and I work in, I had doubting Thomases, and so out there in the Dan and Stan site, you'll see a video out there, and I think Stan, you got that? Was it efficient compression of 50,000 psi or something like that? It's the video. So you can actually watch this in real time. And I put an analog meter there, and everybody's like, well, Dan, you should have went above 5,000 psi. Well, those analog meters, they only go up to 5,000 psi, and I've blown up about 5 or 6 of them actually figuring this out. So it's actually a very dangerous form of compression, because it'll go from nothing to 5,000 psi in seconds, and things at that pressure kind of fly into pieces. I'll put it that way.
Yeah.
So
fair enough.
Yeah. So when you look at how much energy it takes to compress these gases, so if your big difference is mechanically compressing hydrogen to 350 bar, that's 5,000 psi, if you didn't know that, consumes 1.2 million joules per kilogram. But fluidic compression of hydrogen to 350 bar consumes only 32 joules per kilogram. So there's this Grand Canyon in efficiency and compression. It also tells you why I can go from 0 to 5,000 psi in 15 seconds, because you're dropping almost like a 9-volt battery of energy into the equation, and you get these huge results. So all that means is with mechanical compressors, you're working against the physics, where I'm using the physics to my advantage. And it really takes a lot less energy to do this than what you would think.
Wow. Well, that's really impressive. And so which fluid are you using? One of the trihydrogen?
Hydrogen.
You're using hydrogen as the fluid.
When you compress hydrogen to 185 psi, it turns into a fluid. It's like butane or propane, it turns into a fluid. Well, hydrogen does the same thing. So when I do my experiments, I use a proton exchange membrane electrolyzer, and my PEM will output 200 psi hydrogen as a fluid that I use. And from there, I can use that fluidic compression to go up to 150,000 psi.
So the key is a critical fluid as opposed to liquid hydrogen, which is like minus 260 C. This is not liquid hydrogen. It's just hydrogen in a fluid state, a critical fluid state.
You're compressing it into a fluid state. You're using high pressure to compress it into that state.
Okay.
And as far as scalability, I'll go to the next slide here. So the above to the right is a prototype electromagnetic compressor power supply using a 3,000 liter tank on the left. On June 17, 2021, I blew out a coupling at 3,970 bar. That's over 57,000 PSI. The cracker unit image below it depicts here has a storage capacity of 15,000 liters. That's a cracker unit from a catalytic cracker from an oil refinery. I was able to verify its ASME certified rating. Both tanks are ASME certified to 5,173,000 PSI with 360 steel liners. The electromagnetic compressor was built. All the IP is owned by Electrum Power and Technology. So I put that in there because people ask me if I patented. The answer is no. This is protected by basically corporate espionage laws under the United States. And of course, this is associated with DARPA. DARPA provided the funding. We actually did the experiments. One of the best things about doing stuff for the Department of Energy, they actually let you keep your intellectual property versus the Department of Energy. If you take grant money to the Department of Energy, they make you sign away all your intellectual property. So, kind of a side note.
So you have the plans for this?
I've already built it.
You've built it. Obviously, I mean, you've tested it.
Remember that high pressure. Remember that valve that's ASME certified, 150,000 psi. 150,000 psi. How do you think that was certified?
Mm-hmm. Oh, okay. So with your help.
Yeah, yeah. That's what I'm trying to tell you.
Cool.
Yeah, this didn't exist. Before 2019, this compressor technology didn't exist. They were burning up the service stations out in California because we hadn't solved this compression problem. That's what I'm trying to tell you.
Okay, cool. And so this is what your company makes, or?
Yes. Okay. I'll show you what we make or what we you know. Okay. I got a project going on right now, but that's beside the point. Let's go in the next one. So why we basically attacking these higher pressures, and I'll show you why.
Mm-hmm.
So there's a 2021 Toyota Mirai. You got there 1 kilogram of hydrogen is equal to a gallon of gasoline energy content. The source is the Department of Energy. Why would you pursue higher pressures? The above depicts a 2021 Toyota Mirai car. Toyota publishes an instruction manual on how to remove the Type 4 carbon tanks from their car with details on how to order all prescribed tools. So in theory, by replacing the Toyota's carbon fiber tanks with higher capacity tanks, greater refueling capabilities could be obtained. So you've got there the Type 4 tanks that are all making car. I've bought 4 used Toyota Mirai cars. What I do is I strip them down. I mount all the parts on a trailer. I sell this hydrogen generator to mainly surgery centers at hospitals. They mainly like it because they can actually roll this inside. Since the output of the fuel cell is only water, they don't have to worry about it being toxic. The other thing is you put hydrogen gas in a tank. The record so far is 7 years without leakage, and of course hydrogen doesn't break down versus like diesel and gasoline. Those fuels break down in storage. So like that's the reason why. But anyway, you can go from according to Department of Transportation, your Toyota Mirai car Type 4 tanks, your round trip mileage of 402 miles. But if you swapped out the tanks for the Type 7 tanks, you can increase the range of the car up to 1,600 miles just by doing the pressure thing. So
right, yeah.
By using the average gas storage well containing 440,000 kilograms of hydrogen at 1,000 bar, electromagnetic compressor using a 15,000 liter tank, what you do is you would normalize the pressure between the well and the tank, so that way you'd have. So that way the tank would have hydrogen at 1,000 bar. At 1,000 bar, the tank would contain 1,200 kilograms of hydrogen. You would then the tank would then be pressurized from 1,000 bar to 3,000 bar within about 5 minutes. We already know that because we've already tested it. Over 50 Toyota Mirai cars could be refueled to 2,800 bar within 30 minutes. So that's a lot of cars that could be refueled. Actually, the part of the process that takes the most amount of time is electrolysis. So 1 million watts per hour produces 22 kilograms of hydrogen. So the compression doesn't take the time.
Okay, down in 2,800 bar or 2,800 bar pressure is how much in PSI?
42,000 PSI.
Okay. So you take 42,000 PSI tanks, put them in an airplane, and it's fairly lightweight fuel. And now they've got engines that either a regular gas turbine can burn hydrogen, but they are now coming out also with electric thrusters. that you could again turn this into electricity and make electric engines for jet and replacing jet engines. Things like that. The technology is just mind blowing.
Mm-hmm. Yeah.
Yeah, we're moving to a place where we're using a lot more drones. One of the problems I know the Air Force has to deal with is actually getting enough flight hours, because we're using a lot more Predator drones and those type of things forward in the battlefield, and also space technology. I mean, we can, scan a deck of cards, from orbit basically. So we're just not using as many troops. We're not using them as like tanks and things like that. The truth is, the M1 Abrams tank became obsolete 25 years ago. The Russians developed this rocket called the Coronet E that's pretty good at burning holes in M1 Abrams tanks. So the age of tanks is basically, we're back to World War One. That's what I was talking about. What the Ukraine war, what's happened over there. The Russians haven't gone any farther. The Ukrainians haven't gone any farther. They fought each other for a standstill because of the satellite technology, because we got drones that will chase a person down and blow them up.
Mm-hmm.
So we're stuck again, is what I'm trying to tell you. So somebody comes up with a major breakthrough. But the point being is, if we take the technology and put it like in cars, instead of once a week refueling your car, you can refuel your car once a month.
Wow. Yeah.
And then if you throw that into military aircraft vehicles, like that Koenigsegg Gamera that can drive 325, 25 miles per hour, you got a car that can race at the Indy track and probably never have to refuel because it's got enough fuel in the tank. It can do the entire 500 miles in one fill up. So,
or a Class 8 truck that can haul cargo coast to coast and not have to stop for fuel.
Yeah, we're thinking we'll build refueling centers like in Nebraska and Oklahoma, so that way you could go from the East Coast to the center of the country, then the center country to the West Coast and back. Is kind of what we're thinking. Even though we got the ability to drive from New York to LA on a single fill up for like a Class 8 truck.
So I have a question about this graphic here, and it has the miles per fill up. And then, 1 kilograms of hydrogen is 1 gallon of gasoline. Now, a gallon of gasoline is about like 4 liters. But I know that, like my car, for instance, it goes like 10 kilometers per liter. So, are you saying 1 kilogram of hydrogen is equal to?
I'm not saying it. I'm saying the Department of Energy has that statement.
Oh, okay. They have that statement.
I have a PDF. It's got like a little quick answer thing about hydrogen, and that's the Department of Energy, their statement. That's why I say source DOE. So I'll send you a little thing that says 1 kilogram of hydrogen is equal to in energy content. It doesn't about mileage, just energy content.
Oh, okay. It's just energy content, but then I guess the hidden information is the fact.
Now, efficiently getting at that energy, that's a different story.
Exactly. So you actually get
the fuel cells are really efficient, 80-90% efficient.
Yeah.
To give you an idea, in this space, actually, one of the leaders in electrolysis is actually Cummins, the diesel engine manufacturer. Cummins has a proton exchange membrane electrolyzer. 1 million watts is 33 kilograms of hydrogen. And how they're able to do that is they accurately control the temperature in the electrolyzer. It was like, why would a manufacturer of diesels be interested in it? Well, so if you look up hydrogen Cummins, you'll find it. But basically, Cummins, and understand Cummins, they're in Columbus, Indiana. They're about an hour south of my house here in Indiana. So what Cummins has, they have all their engines. They have your 6 liter and your 8 liter and so forth, but they have 3 different engine designs. So one burns diesel fuel, the middle one burns hydrogen fuel, and the last one is compressed natural gas. And if you want to know what Cummins is doing, is they're focusing on the hydrogen, because the pressures and tolerances and all the molecular aspects are higher in the hydrogen, and anything they develop with hydrogen burning in a diesel engine, guess what? It works for natural gas. And remember, natural gas turns into supercritical fluid at 900 psi, so it's a lot lower pressure. And if you say, why is Cummins thinking about this? Well, look at all the compressed natural gas buses like out on the West Coast and out on the East Coast, like in New York and Boston and those places. And that's what Cummins is thinking about. So one of the big leaders in this whole space is actually Cummins and their diesel engines.
Mm-hmm. Wow, interesting. Thanks.
Okay. And remember the Type 6 tanks and Type 7 tanks? That's to be tested by the Department of Energy. Right now, our federal government is in complete chaos. I have no idea when that's going to happen. But also remember, there's already a Type 5 tank out there. It was certified in 2010. So it means that Toyota, they could be upgrading those tanks And Stan, do you want to talk about the refueling issues that are going on?
Well, when you're using hydrogen as a fuel for transportation, the speed with which you refuel and pressurize the car tank has to be managed, because as you compress the gas, it heats up, and that causes issues with the tanks in terms of cycles and damage to the tanks over time. So you have to control the fueling process, where you're either pre-chilling the hydrogen before you push it into the car, and you have to monitor the temperature of the tank in the car as you're fueling. So there are issues like that you have to be careful of. But again, with Dan's compression, um, there's just things we can deal with, but it may not calculate exactly as people think. But bottom line is, you can fill a car to 10,000 psi in probably 6 minutes, just similar to what it would take you to fill a gasoline car at ambient pressure and temperatures with regular gasoline. So we start from there and say, okay, but when we do go to higher pressures, we may have to slow down the refueling a little bit to keep it safe, or pre-chill the hydrogen as we're pushing it to increase the speed at which we can refuel. But those are surmountable issues.
When it comes to fluidic compression, the process actually dampens Brownian motion. What that means is the gas doesn't get hot. The power supply in the system gets hot, but the gas doesn't, because it squashes Brownian motion. But one of the issues we're dealing with, my good friend Chris McWhitty on Millennium Marine Energy, Chris actually makes refueling stations, and he wants to be able to refuel cars at 350 psi. It has to do with 350 bar, because that's what the customer wants. But Toyota wants everything fixed at 700 bar. Obviously, I'm against it, because I think a customer should have the option of refueling their vehicle up to 350 bar all the way to 2800 bar. The customer should have that as a choice. But Toyota we're not going to move from 10,000 psi and go anywhere else. So that's one of the issues going on in this space. It's not what you would think. It's like, well, you guys have gotten all the way to this area, but yeah.
Yeah, because like everything else in a complex system, there's other critical points where a business has to look at costs, or a business has to look at production, or a business has to look at your manpower and what they can do. And Toyota doesn't want to make, even when you look at the military, we're all about logistics. The Defense Logistics Agency doesn't want 6 different kinds of fuel and 6 different kinds of equipment. They've got one kind of jet fuel, JP8, period. It goes in Abrams tanks, it goes in airplanes, it goes in generators, So again, when you get into the business side of this, although it's technically possible to do all this stuff, we have to accommodate, all the other inputs that go into industry and production and moving and logistics and things like that.
So it would make sense to just go over to everything uses hydrogen.
Yeah. So we'll go to the next one here. Any more questions on this yet?
No.
Okay. So becoming ubiquitous. So the top is the original tank that the Department of Energy developed. It has a device in it called a BOSS. So that way, if it encounters high pressure or abnormal pressure readings, it basically will open up and release all the hydrogen to the atmosphere before anything dangerous might happen. The floor tank, that's from SpaceX. It was built in the Heavy. They've got a bunch of, they think those are 6-foot midgets down there. So it's bounded to pressure and size. These high pressure carbon fiber tanks are almost bulletproof. To rupture a carbon fiber tank with an armor piercing military round requires the shot to be perfectly flat. Otherwise, the flexibility of the carbon fiber will repel the round. So I got a lot of people say this is not possible or you can't do it. And I'm like, oh boy, you don't know. I mean, you just don't know where we've gone with this. We've kind of trotted along at warp speed. We're probably beyond what most people think we are.
So the most efficient vessel to hold high pressure is a sphere, and everything a little bit less than that, like a cylinder or that shape that he had in the bottom of that slide, is basically a modification of a sphere with all round corners. No square corners, because that weakens the structure. So you kind of have that limitation. But imagine if you had little tiny bowling ball size or smaller tanks, and you could arrange them in any way you want in a car and not take up a fixed space underneath the car that's 20 gallons. You could put that behind the back seat. You could put it around the side where you can't put your golf clubs anyway, and things like that. So we just have to start thinking a little bit more out of the box for solutions going forward.
And actually, related to this, I had a question. Have you asked Elon Musk for his 2 cents? Because he had the SpaceX there. I don't know.
Elon Musk has coined the term fuel cells instead of fuel cells. He hasn't been historically a big supporter of hydrogen, but I think that's one that's going to bite him, because as a space guy, he knows that you don't put rockets into space with gasoline or electricity. So he understands hydrogen, but I think, again, this gets into the collateral damage. When you're making electric cars, you probably don't want hydrogen competition. So I think that early on his feel of hydrogen was, it's competition. I don't want to promote it or support it. But I think he's probably at some point going to have to admit that hydrogen storage is much more efficient than battery storage.
The only thing keeping that Koenigsegg Gemera from becoming really serious competition for Tesla is the fact they're $10 million a piece. But if you manufacture cars like that, those cars will smoke Teslas any day. It's 325 miles per hour top end. That's insane speed. This tank here is actually designed to hold LNG, liquefied natural gas, for the heavy when they basically launch it in orbit.
Okay.
Yep.
Oh, I see. So you're saying those fuel cars, fuel cell cars are very expensive?
No, not necessarily. The Toyota Mirai, you can buy a used one in California for $6,000 or $7,000.
The four of them I bought them for $15,000 each, and the reason why is the Toyota Mirai has a 114,000 kilowatt fuel cell in it. If I try to go out and buy, like the Nell, to buy a 100,000 kilowatt fuel cell, it costs me $100,000. The cheapest thing to do is buy a used Toyota Mirai car, used with Toyota's basically extended warranty, and just tear the car apart and mount all the components on a trailer and use it as for generating electricity.
Toyota has gotten the cost of building fuel cells ridiculously low to the point where it makes sense to put them in cars.
Yeah.
Oh, okay. So
not only that, but they gave away the technology. It's all open source, so they're not hiding anything. There's nothing proprietary about what they're doing.
So how much does fuel cell cost new? Like
Toyota Mirai right now in California, they lease them, but the stated MSRP is around $56,000.
Okay, I see.
Which is not out of control, compared to other, mid-range, mid-size, cars. And it's nice. The new ones are really beautiful looking cars, and they're real competitive. I think as the industry starts adopting this hybrid technology and fuel cells, it'll get cheaper and cheaper, and probably even drop the price in cars at some point.
Mm-hmm. And then I guess a related question is about that Bezos. He's big on hydrogen for his rockets. Do you have any comment on that with this Blue Origin, the penis ships, or I don't know. No?
Well, basically, NASA's been using hydrogen for their rockets for decades, many decades. It makes sense because of the energy density. Like I said, in Hawaii, we say hydrogen is very energy dense, but it's very fluffy. So, you've got to compress the living daylights out of it to get it into a small enough container where you can move it around and carry it with you. Because like Dan says, what a kilogram of hydrogen, how much? 12,000 cubic
12,000 liters, yeah.
Liters. That's a lot of volume. Yeah. So you got to compress the daylights out of it to make it functional. And Dan's compressor that goes to 50,000 psi there's your answer right there.
Right. Cool. All right, Dan.
Yep, can do. We'll go to the next one. Let me put some of these pieces together and show you the what can be done. So so you've seen this graphic before. I use it as the logo for the company. So that's basically the hydrogen economy. So basically it's going back to the old town gas system that existed here in the United States before 1966. The above system is designed to replace the energy infrastructure for a county. The system plans on using a secondary heat exchanger from geothermal power for heat exchanger from the geothermal power plant provide district heating for a town to remove counties off the gas grid. The system allows towns to remove from the power grid also by directly plugging into a substation. If you use the 100 megawatt per hour option, that's enough electricity for 50,000 houses. 220 megawatts, that's enough for 100,000 houses. So you're talking about towns with populations probably closer between up to 300 to 400,000 people in a town. With the hydrogen part providing transportation, refueling, and backup power via gas turbine, minimum cost per county at 2025 costs is $130 million per county. There are 4,063 counties in the U.S. It's been calculated that only 720 are critical for maintaining the economic viability of the United States. The 720 counties would be next to major freeways and thoroughfares within the country. For 720 counties, total cost is $93 billion. If all 4,063 counties were converted, the cost would be about $580 billion. This is distributed energy system. It kind of goes back to the old town gas system. And also remember, they're planning on spending $5 trillion in that CO2 pipeline system, trying to leach the last of the asphalt out of the ground.
So this would be a lot cheaper, 10 times cheaper.
Yeah, a lot cheaper. Or think about $2.3 trillion for all the refineries or all the natural gas grid they got built across the United States. So that way each county would be completely independent. Like I said, you would have a geothermal power source would be base load, backup power from gas turbine. You would store, like I said, each gas well averages out to 440,000 kilograms of hydrogen at 15,000 psi at the gas well. And of course, the compressor compress it up to 3,000 bar for refilling Toyota Mirai cars and that type.
Yeah, I'm not sure if what Dan said got past everybody, but they're planning to build a transcontinental CO2 pipeline grid. And the only reason they're building it, they're saying it's to sequester carbon for greenhouse gas reasons, but it's really to pressurize oil wells to get the last of the oil out of the ground in fracking areas. And with the money that we're going to spend on that CO2 pipeline, which is also, by the way, very dangerous, it's already killed people when it ruptures and in the farmlands and stuff. It's a waste of money when we could be investing in Dan's model.
Yeah, wow. And understand I'm talking about things, like I said, we had the military, we have 22 projects out west that have varying pieces of what I'm describing here. So,
and so what's the closest to like a complete model? Like you have a hydrogen economy here.
I have a project up at Columbia, right, that we're basically working on the project. So install the gas turbines, and I've already had the wells drilled. And right now, the customer is trying to determine whether they want to use town gas, meaning syngas production, or whether they want to go directly to electrolysis. And that's what we're going through right now. The customer has a need for carbonated water, CO2. They're in talks with Coca-Cola. So they're going to use, they're thinking about using biomass basically to produce, biomass of water to produce hydrogen and carbon monoxide, turn that into carbon dioxide through water shift. And that way, that carbonated water, they can use it for a Coca-Cola plant and then store the hydrogen underground, burn in a gas turbine, and actually start purchasing fuel cell vehicles. But we're in that stage. So like I said, we've already got the gas turbine. We built two LM6000 gas turbines. The compressor's already there. And right now we're in the process of putting together the gasifier. I'd rather them do electrolysis, electricity and water be simpler, but they're trying to pursue this the gasification of biomass thing.
So Andrew, as promised, we've blown through your 1 hour time limit.
Yeah,
2 hours and 18
2 hours.
2 hours, yeah.
Yeah. Well, it was a 1 hour, but it's been over 2 hours. But actually, I have a follow-up question because here in Grey Bruce, we have the largest operational nuclear power plant in the world, and it has a lot of extra power. And we also have Hydrogen Optimized, which is the largest hydrogen producer. And so what other aspects would we need to add in order to, I guess we would need the compressor, and
the compressor's already been designed and built. That's what I built the electron hydro compressor for.
Yeah. So we would need to be able to store large quantities of this.
Like I said, the average gas well is 440,000 kilograms of hydrogen per well.
Yeah,
It's
just
money.
I don't know if we have any gas wells or anything around here, but we have a lot of
I can drill
limestone.
one. I can always drill a dry hole, Andrew.
Okay. Okay. And how much would that store?
The wells I drilled up in Colombia were $2 million each.
I mean, how much would it store?
440,000 kilograms.
440,000 kilograms. So that's 440 tons. Yeah. Okay. And okay, that's quite interesting. Well,
I'll go into the economics and I'll actually break down the cost for you. Okay.
Okay.
We'll go to the next one. You guys are asking.
Oh,
good
okay.
questions.
Okay. Oh, okay. There's more. Okay. Go ahead.
Be patient.
Sure.
Okay. So I bring this up here because I've got some folks, some credentialed folks out there that get a key important thing wrong. Okay. And what it is. So this is a hardbound book. It's an autobiography of Professor Fritz Haber, right? It's in German. I've got an English translation also, but I actually bought this hardbound book. So in section 5.2.2, diammonium synthesis, basically the synthesis of ammonia, what it is, page 151, and you can use Google Translator on your phone to translate what the professor says about producing ammonia. And that is, the process prefers higher pressures at lower temperatures in the presence of an iron-based catalyst, right? So I have credentialed people that get this wrong. They put these sentences together to say, using high heat and nitrogen and hydrogen, you get them bond together to make ammonia, and you're completely off the planet with what you just said. That it's pressure and a catalyst that produces ammonia. It has nothing to do with the heat. So in the process that they use for making ammonia, they have to heat the catalyst up to 450 degrees Celsius because the pressure is too low. It's not the heat that makes the ammonia, it's the pressure and the catalyst. The other thing they get wrong is the catalyst itself. They'll say that it originally used osmium uranium to make ammonia. No, that's not correct. The catalyst was 97% iron, and it was 1% osmium and 2% uranium. So there were actually, less than 3% of it was these rare materials, but 97% of the catalyst for making ammonia was actually iron. So those, like I said, we've got credentialed people that are writing white papers that are getting things really, really wrong. So.
And Dr. Harbor there, Fritz, old boy, he's not related to Dr. Evil.
he's not a new guy. The other thing people got, he's a chemist, won a Nobel Prize, but you can see down there, he was also a Jew. So you can't say he was like a Nazi or something. This guy was a Jew. So
he created the Haber-Bosch process, which
yes, that's what I'm talking about. That's the synthesis of ammonia. He's giving you the secrets how to make ammonia. It's not the heat; it's the pressure and that iron-based catalyst.
Iron.
Yeah.
Yes. So is it any iron or is it a special iron?
Yeah. The truth is,
alloy?
I don't know what it is, but I know the company that makes it, and I know it's $1 a pound, and you can get it in 100-pound pails of these iron pellets. Yeah.
Oh, that's the catalyst.
Yeah, I don't know how to make it. I know somebody who does make it.
So, and it's cheap. Okay.
I'm not going to make it when I can buy it from somebody. Why would I make it?
So. That made the nitrogen fertilizer, which made the green revolution possible, which is the reason why we're all here.
Well,
yes,
exactly. We're talking about like anhydrous ammonia. We're talking about a critical. But I'm just saying we have people writing white papers that are getting this important thing wrong. Is what I'm trying to tell you.
Yes.
Okay.
Yes.
And that's why Charlie's worried about us overpopulating the planet because we can keep going through.
Even though China's population is rapidly shrinking as we're speaking. So. And Japan's got some serious demographic problems. So we go to the next page here. So ultra pressure Haber process. So the Haber process prefers higher pressures at lower temperatures at 1000 bar. The Haber ammonia reaction occurs at 23 degrees Celsius. So that's 70 degrees Fahrenheit. That's room temperature. And 90% of the nitrogen and hydrogen transform into ammonia. The reaction is exothermic and therefore requires heat exchanger to maintain the lower temperatures. The company that produces it is PGT Chemical. So it's www.ptgchemical.com. And they're down in Tennessee. So I don't know how to make the catalyst, but I knew where I can buy it from because I got a plastic tub full of the stuff. Just so I can do some experiments because since I've got ability to make high pressure hydrogen, and I got a compressor that can compress air to make liquid nitrogen or fluid nitrogen, however you would call it. But anyway. Okay.
Wow.
So why is this important? So here's the next slide. So this is a modification to the plan, to the hydrogen economy that system you built for a county. Since the iron-based pellet catalyst for the harbor reaction is inexpensive, it's $1 per pound and easily available. An electrum hydrogen park with a harbor mod could be deployed in farmland. The source for the nitrogen would be a mechanical compressor with desiccator. The mechanical compressor would air to 550 psi, nitrogen fluid at 495 psi. This would allow the farmers to produce only the required amount of anhydrous ammonia needed for crop planting. It's estimated that 80% of the year, the harbor equipment would remain idle, thus would reduce, if not eliminate, the risk of transporting anhydrous ammonia via rail or ship. So it's a way of more efficiently applying ammonia to farmland, not transporting it from one side of the planet to the other. Because it's mainly just hydrogen and nitrogen, and if these guys have farm equipment, tractors that are powered for the hydrogen, we can just add some equipment on there to produce anhydrous ammonia, and therefore it would go from the park directly to the field, and each county would be completely self-sufficient in farmland.
So let me clarify there. Are you saying on each tractor or each county would have one of these ammonia?
Well, understand if the farmers are using like the JCB tractors that have the diesel engines that burn hydrogen, and understand Lord Banford, he sells equipment for farmers, all right? And understand, remember Cummins diesel, they're making diesel engines that burn hydrogen. That means we can convert farm equipment over to using hydrogen rather than diesel fuel. And what I'm saying is, if you placed a park in the middle of the county so they can get this fuel for farming, we can also produce the ammonia. So that way they're only using the amount of ammonia necessary to plant their crops. And that way you have this distributed infrastructure. We're not dependent on some specific ammonia plant and the whole thing blowing up. The other thing too is, since the ammonia is being produced at a much lower temperature, right, it's a lot safer to handle. At the ammonia plant, when they heat the harbor reactor up, it's 450 degrees Celsius. Well, ammonia at 450 degrees Celsius, when it comes in contact with the air, it ignites, and sometimes those plants blow up down in Texas. Right? Versus if you're producing your ammonia at room temperature, those temperatures aren't there. You're not going to auto-ignite the ammonia and cause an explosive situation. So it's just safer all the way around. You're using lower temperatures, and you're only producing the amount of ammonia necessary to actually plant crops and produce food. So,
and the little arrow that goes from that ammonia production to turbine in the system is another gas turbine that runs off ammonia that can make electricity, et cetera, et cetera, et cetera. So again, it can be used for jet engines, things like that.
Yeah, the LM6000 gas turbine will burn ammonia directly. So it's one of the things, part of the project there at General Electric when I was working on alternative fuels program was hydrogen, ammonia, DME, to make sure we programmed the fuel control program to burn all these different kinds of fuel. I know that international shipping, they're looking at using ammonia in ships, and they're going to burn in a gas turbine to drive a generator or to drive induction motors to move the ship. So we'll see how it all plays out, though.
I know generally farmers don't use straight ammonia. They use like ammonium nitrate pellets, but you could make them just with...
Well, the farmers here in Indiana, they use anhydrous. That's what they call it.
Anhydrous. Okay.
The guys here don't use ammonium nitrate. They use anhydrous. They have those big trailers. It looks like a propane tank. You can compress ammonia into a fluid. It's the same pressure as a propane, but they have those trailers that they drag around here in Indiana. They grow a lot of corn here. They use a lot of anhydrous. They don't use ammonium nitrate.
Oh, so that's the liquid form, and they just spray it on the field?
You can compress ammonia into a supercritical fluid. That's about 124 psi. It turns into a fluid, and you can put it in that tank. And so around here, you'll go out there and you'll see a big tanker thing out there in the farm field, and like, oh, that's the anhydrous ammonia. It's not propane or some other fuel. That's anhydrous ammonia is what's in that tank.
Okay, cool.
It's a gas. I mean, anhydrous means without water. So it's ammonia gas without water, anhydrous. They call it, the term they use is, they call it anhydrous is the term they use. So I don't know about up in Canada. Down here, they don't use ammonia. They try not to use ammonium nitrate because it's a safety issue.
Oh, I see.
Especially if you've got a barn catching on fire, you might get an explosive event, which has happened before. There's been some exciting energetic events down at Corpus Christi, loading up ships full of ammonium nitrate and they're blowing up. I think a couple years they had one there in Beirut. Some big warehouse for ammonium nitrate blew up. It was pretty spectacular. But the point is the anhydrous is a lot safer to handle. It's toxic, but it's safer to handle. The farmers have learned how to use it around here. They don't use ammonium nitrate.
Oh, okay. Okay.
Makes sense?
Yeah. So you're saying it's
well.
safer,
The other thing too, if you've got the
blow up.
machinery, you could use this to make ammonium nitrate. But understand, I'm just using the bare minimum equipment to make.
No, that's fine. So that's great as long as they can use it. I'll have to double check with my farmers.
Yeah, like I said, you can add machinery to us to make like urea and things like that, but it's more machinery versus I can just use the bare minimum round of machinery, which is the electrolytic compressor, a mechanical compressor for making the nitrogen, and you can pump that into that big tank, fill that iron catalyst, and just produce anhydrous ammonia directly. It's a simple process. But if you're doing something more complex like ammonium nitrate or urea, that requires a lot more hardware. So, so that's safer just to make anhydrous and.
Okay, sure. And then
it's a gas, and you can apply it to the fields. It's a lot more efficient.
And then apply it. Okay.
That makes sense?
Yep.
Okay. We'll go into the costs here. So this is a tool that was developed by Sandy National Labs. It's based off population, right? So you plug in the population of your town, and they use the Department of Transportation numbers to figure out how many vehicles, passenger vehicles have, how many trucks you have, that kind of thing. And so, for example, I'd like to use Houston as an example. So let's say I wanted to have 10% market penetration for hydrogen fueled vehicles. That's fuel cell or diesel burning hydrogen, whatever, right? You would have to have 30 megawatt grid scales electrolyzers basically scattered around Houston to do that. If you wanted 25% market penetration there in Houston, you would have to have 80 megawatt grid scale electrolyzers to do that. If you're doing 100% market penetration, that'd be 300 megawatt grid scale electrolyzers to do that. That would require a generating capacity of 301.69 megawatts of electric power. You could probably build two 220 megawatt geothermal power plants to provide all the transportation fuel for the city of Houston. The other setups are depending on geology and the wells and some other factors. So.
Okay.
Yeah, LA is probably the hardest one to build out.
So I don't see any kilograms of hydrogen per day. Okay, I see. Okay, yeah. I just wasn't sure.
It's based off the old town gas system. If I'm basically turning, basically how they did the old town gas systems. But Los Angeles, that's a tough one. Yeah, it's almost a gigawatt worth of power you'd have to come up with.
Right. Okay. And so would this be more or less electricity than they're using now? Well,
it'd be more efficient. Yeah.
Okay.
Yeah. And especially if you're using geothermal as the energy source. Remember, Houston is a city spread over a large area, and a geothermal power plant, like I said, if you got a Walmart parking lot, that's the size you need to build the plant. So they're not big plants, but like I said, it's a distributed energy system. It's not like the county-based system. This is basically you're trying to retrofit the energy system for a city. And the next one I'll go into, what does it cost, for each. So,
okay.
So this one here is based on, so the cost driver is the wells. Deeper wells store more kilograms of hydrogen, which leads to lower number of wells, less cost per kilogram delivered. CapEx with maintenance operation. For the Houston setup is 40.5 cents per kilogram with 40.5 cents profit per kilogram. Taxes projected to be 18 cents per kilogram for a total cost of $1 per kilogram of hydrogen delivered. And if you're building a system for Houston, the cost would be $520 million to build this system for Houston. And of course, you get down there toward Los Angeles, you're approaching $1 billion to build this system for Houston. So basically, the deeper the wells you drill, that means you can store more hydrogen. You actually have fewer wells. Fewer wells means less infrastructure that you have to put in place.
Okay.
Like I said, this is a tool that Sandy National Labs developed. You just plug in population, boom, here's what it'll cost. And I put in all the cost data that I use when I'm putting the systems, and it comes up with these numbers. So.
Yes. So for like 100,000 people, you'd be spending $130 million.
Yeah.
Yeah.
It's economies of scale. There's like a bare minimum, the smaller the population, the higher the cost,
Oh,
So I
right.
got
Yeah.
117,000. Remember, $130 million per county, and that's assuming that you've got a county you're right. That could be a maximum of 200,000 people in a county. So
Okay.
yep. So, and I got the last slide. Are you guys ready?
Sure.
Okay. So it's been a long one. So Baltimore
Yes.
converted their street lanterns over to electric in 1970. The Baltimore Gas Light Company was providing town gas to the city of Baltimore over 150 years ago. It's 1,200 gas street lights and 427,000 homes in 1969. Get that. The gas lantern gas lantern is on the National Historic Registry. It's a National Historic Landmark. The city has installed security cameras all around the lantern. I'm sorry, just a second.
To
It's
discourage
just as important as the
vandals and
Washington
stuff.
Monument or Mount Rushmore. They conduct a gas lantern holiday every February 7th. The Baltimore Gas Light Company was founded on February 17, 1817. They still burn town gas in this lantern. They've been burning a hydrogen mixed gas in this lantern for over 2 centuries. So I have people that say you can't do it. Well, I hate to tell you this, but in Baltimore, there's this national monument that's been burning hydrogen for 2 centuries. And if you look up there, it's got these little mantle things. It looks like a little, if you ever had a gas lantern, it's got a little cage thing, and you put this cloth sock sort of over it and you tie it off. The ones I have thorium in it, but they also use rare earths in there. Basically, you fire up the gas lantern, you put a match to it, and you burn off all the cloth, and it leaves behind this shell. So when the gas lantern went at nighttime, they turn the gas up, and it gets really bright. It gets so bright you can't look at the gas lantern. So it's actually that shell that's glowing. The hydrogen, when it burns, it generates ultraviolet light, but that gas lantern basically turns that into visible light. So it's a much different kind of lighting than what you're used to electric. You'll be rather amazed. What are the issues with oil and gas industry? When it comes to oil fields, the last thing that passes through the wellhead is natural gas. Saudi Aramco currently has this hydrogen project where they are trying to transport hydrogen from the Middle East to Japan. First, they perform steam reforming. They take a pipe full of nickel ball bearings and heat it to 500 degrees Celsius. Then they introduce steam and natural gas to produce syngas. They then use water shift reaction to remove the carbon monoxide. Carbon monoxide, water, iron, chrome, catalyst are converted into carbon dioxide. The carbon dioxide likes to stay dissolved in water, forms carbonated water. The hydrogen then cryogenically frozen down to minus 250 degrees Celsius. That's minus 423 degrees Fahrenheit. Until the hydrogen is a liquid at room pressure. They freeze that gas down into a liquid at room pressure. This cryogenic hydrogen, it is transported from Saudi Arabia to Japan. This project is absurd on 3 levels. The first is the cost. The cost is $150 per kilogram. Second, Japan is surrounded by an ocean of hydrogen, and you wouldn't believe how much rainfall they get. And the third is, why would you transport a substance that covers 70% of the earth from one side of the world to the other? The oil and gas industry is an industry that takes a finite substance only found in certain places of our world, refine it as some great products like diesel and gasoline, and then ship it to the other side of the planet. Why would you try to ship a substance as ubiquitous as hydrogen from one side of the planet to the other? So when these guys are saying you can't scale it, no, what it means is the oil and gas business, they can't scale it. That's all that means. It doesn't mean it's already been scaled. And a good example will be like Baltimore, like this gas lantern that you can't make go away. It exists. It's been burning hydrogen for 2 centuries. I went to 15 years ago, I was on a tour there in Baltimore. And so I got pictures of me standing at this gas lantern. And I asked the tour guy, and he told me that they converted the lanterns over to electrical in 1970. I said, so you guys still got a gasifier? I said, what, propane, natural gas? He said, no, we still got a gasifier. I said, what are you guys using? He said, wood. They're using wood as a source material for the syngas for this lantern. So they've been burning hydrogen and carbon monoxide in this gas lantern for 2 centuries. On the left-hand side is a cooking stove. In England, they converted over to natural gas in 1970 when they discovered the North Field oil field. The North Sea has gone into terminal decline 20 years ago. So the British are actually thinking about going back to the old system. Everybody thinks they're crazy because they're talking about going back to hydrogen, but you're not realizing that the old town gas system is still there. It didn't go away. All they did is took the pipes going to the houses, they cut it off and put a cap on it. All the infrastructure's still there. So that's why the British are kind of thinking this way. Are they going to go back to gasification, or are they going to use electrolysis or steam reforming? They're not quite sure. But that's why the British are thinking this way. The other one has to do with the Germans. I mean, before 1970 in Germany, there were 350 gasifiers all over the country, hamlets and villages. So I have this subject, and you kind of need to kind of rethink what you're doing, because if you come across legislature like in Maryland, they're going to laugh you out the door. If you show up in Indiana, they're going to laugh you out the door. Lord Banford, they're in England. He's a member of the House of Lords. So is his dad. So is his grandfather. So is his great-grandfather. And there's a lot of those lords that had businesses from the old town gas system. So if you show up in England and start talking about embrittlement, leaking, and all that stuff, they're going to laugh you right out of the place, because obviously you're missing some history. So that's my presentation, guys.
Okay. Wow. Well, that's amazing.
Thank you.
And if you think Dan is really smart, I think it was Orson Welles said one day we're gonna use water as fuel. And how long ago was that? A couple 150 years ago.
Well, we figured that 400 years ago. We figured out how to turn coal and water into a fuel. That was the town gas.
Yeah.
416 years ago. So it's been figured out.
So miraculously, Andrii, we've turned a hour-long briefing into 2.5 hours for you. We crammed it all in there. I'm glad everybody stuck around for it. But Dan is an amazing guy, and I just love listening to him talk about this stuff.
It's awesome. It's awesome. It's really interesting. I was wondering the feed for all this. I've heard that you can use offshore wind, and you can through electrolysis you can make some hydrogen and put it in like a tube, and then the hydrogen will go up to something on the shore, and then that could be used as a fuel also from offshore wind. Is that possible?
That's true. You can go back and look at Dan's slide that shows you the cost of doing offshore wind.
Yeah.
Well, I know it's expensive, but I mean, there's twice. I know
it's possible, but the costs are pretty high. I mean, you talk to Stan, anything out on the water is expensive. The ocean is really hard on stuff, really hard. Oh yeah, and also the cost of doing maintenance on stuff out in the middle of the ocean. So that's the only thing against offshore wind.
So, for example, if you had a pipeline running from an offshore wind platform to your shore, is how deep's the water? If the pipeline ruptures down underneath the water and you have to repair it, it costs an incredible amount of money to get a South Navy salvage team to get out there and repair your pipeline. Things like that are what keeps that stuff in check.
Oh yeah, we were looking at the difference between one side of the island to the other side of the island in the amount of electricity that it would make, and it was double on one side to the other.
It's kind of a complex issue. It's sort of like why Hawaii doesn't have really a power grid where they have power lines between the islands. And it's because essentially each one of those islands is actually a mountain, and you wouldn't believe how deep the ocean is between the islands and currents and so forth. And of course, the ocean's incredibly hard on that equipment. So like in the Netherlands or Amsterdam, their course, that water's relatively shallow, maybe 90 meters deep, something like that. But in hydrogen, Hawaii, that haven't been able to do that because the water's so deep and the currents and the ocean's just so incredibly hard on equipment. That's why Hawaii basically is stuck in a situation where they have to build like this town system I'm describing, where each island has its own independent energy system. Or just like what I'm trying to say with this hydrogen system is focus on the town of Baltimore, or focus on Indianapolis. Don't worry about fixing the whole thing. Worry about just fixing one county and just do it a piece at a time and make them all independent. And that's probably the best way to do this.
Okay. Yeah, the distribution cost of power is a lot higher than most people think. And plus you have line loss, even just transmitting power. And as military guys, Dan and I both know that if you have one or two big targets, you're vulnerable. If you have an undersea cable, you're vulnerable. If you can distribute that system, that generation system, it's a lot harder to target from a military perspective, and gives you the redundancy and the resiliency that you need to keep on going under adverse conditions.
Yeah, that was Smill's idea, was to have very distributed grid. All these feeds, tons of feeds into the grid, houses, everything.
Even an example, one of what the Air Force is thinking about is actually digging a really deep hole, building a geothermal power plant in the hole and covering it up, so you wouldn't even know where it is. And also do the same thing with the wells storing the hydrogen gas. So that way there's nothing above ground and it's not easy to get at, and that's what we're thinking about the military. You building these kind of systems are actually a lot better. One of the things we have to do is provide, like we have these energy drills where we turn off the main line to see if we've got enough generators, whatever, to keep operations running. We're finding out we're pretty deficient. So then you start going to try to figure this out, and you come up with, well, the only one that really fits it is either I spend a lot of money on a submarine reactor sitting in a hole, or I build a geothermal power plant. And so you look at budgets and say, which would rather do? We know how much. I mean, the Navy's been doing small modular reactor for 70 years, so we know what that is. Here's the price of that. It works for 20 years, or I choose this option that costs a lot less, and I can probably keep it running for a couple hundred years. So that's what the idea is that the military is thinking about. It's just a cheaper way of building this. It's just that, like I said, the oil and gas business, there's no way to scale hydrogen for the business they've got. But understand, it doesn't make any sense. When you've got a substance that covers 70% of the planet, why would you bother transporting it? You just make it, use it, consume it locally.
So I have this map of the geothermal maximum aquifer temperature, and it's supposed to give kind of a proxy for the geothermal data. I'm just noticing that it seems to be mostly in like mountainous areas that you have the geothermal plants and things like that.
Yeah. So I have a lot of people that bring that up. Here's how I'm going to answer you, Andrew. Andrew. So what a lot of people do is they try to do this precisely. This is not a precise thing. Use my formula to figure this out. I've already given you the data. I mean, if you want to build district heating for your town, right? That's 6 kilometers. You need to think about drilling wells 6 kilometers, building them 6 kilometers apart. If you're going to build a power plant, it's 11 kilometers. Don't worry about the map. Worry about drilling to 11 kilometers, because the temperatures will always be higher. Okay?
Okay, I see. Okay.
So you can spend a lot of time trying to accurately map this out. And I go, guys in the geothermal business, that's exactly what they do. And they spend a lot of money, a lot of time, and they accurately drill this thing out. And then a couple of years later, something happens to the geology, and guess what? The power plant doesn't work. Versus what I'm showing you, I can guarantee you that plant will produce power for the next 500 years because I've over-engineered it.
Okay, cool. Yeah, because I'm looking at, in terms of the crust thickness, it's definitely less outside the mountainous areas. So anyways, okay, so I think, do we have some last questions? Okay, one of the last questions from the YouTube, isn't ammonia highly corrosive?
No.
Okay.
It's not chemically reactive.
Okay.
And even making ammonia, you gotta have high pressure and that catalyst to make it work.
It's caustic, but it's not corrosive.
It's basic.
Okay.
It's not aesthetic.
I see. Okay, and then they were talking about the energy efficiency of hydrogen, and I got this answer from Grok that it's 60 to 80% for commercial electrolyzers, alkaline electrolyzers 60-70%, proton exchange members 65 to 80, and solid oxide electrolysis over 80% efficiency, 90%.
The problem with that, you've got people making general statements versus if you show up at Cummins, they have an electrolyzer that is 91% efficient.
91%.
So back to the manufacturers.
Amazing.
Yep.
All right.
Product makes a big difference. You can't make general statements about that.
Fair enough. Okay, so I think that's everybody. Any closing remarks, guys?
I have a question, Andrea.
Okay, go ahead.
You record these, right? And how
Yes.
do you get to them if you want to go look at them?
So they are on YouTube, and then you can just look up my name.
Okay.
So which is, or Peak Oil Chat, either one. So Andrii Zvorygin.
I usually look at Andrii ZV, and I find it Stan.
Okay.
Yeah, and then see here we're live. Okay, and then you would go to my channel, and then you would click on the live ones. and then you would see the live streams that I've done.
Okay.
Mm-hmm. I also do a bunch of spiritual live streams, not just peak world chats.
I did never guess that, Andrew.
Oh yeah. Oh well. No,
that's all good stuff, Andrew. All good stuff.
Yeah.
Oh well, thank you. Yeah, it's all about love and kindness, and because that's really what I'm about, is being of service to
being in harmony with the universe. Those are all important things.
Yes,
yep.
Exactly. All right. So as I found you, would leave you in the love and in the light of the one infinite Creator. Go forth therefore rejoicing in the power and in the peace of the infinite Creator within you and all around you, my friends. Adonai. All right. Okay, I've ended the stream.